First of all, we're gonna open your eyes so you can see who you're gonna call if you wanna be free. GLOEBUSTERS! 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 Who you gonna call? Who you gonna call? Who you gonna call? Yeah! GLOEBUSTERs! GLOEBUSTERs! GLOEBUSTERs!
And welcome everybody to GLOEBUSTERS.
We accept the reality of the world with which we're presented. It's as simple as that.
All right, hello and welcome, lads and ladettes, to GLOEBUSTERS, Season 13, Episode 8. Today I'm joined by Shane, and good times for all. Zachary Zambala will be here shortly. Oh, there he is in the audience. I see him. Bring him up. All right, tonight we got a presentation for you guys today on the physical meaning of mathematics regarding reference frames, going all the way back to the Newtonian concepts up to the modern concepts with relativity theory, and what the physical interpretation of what these calculations are supposed to be and where they're supposed to be applied. If you guys want to do super chats, you can go to kofi.com/globebusters, or you can donate on Rockfin where we're streaming, and we'll read those at the end. And then throughout the Prezi, if you guys have questions, make sure to tag either GLOEBUSTERS or at SpaceAudits or at Shane St. Pierre or at Good Times for All or Cami, Aisley 711, I think, or 1777, I think it is.
717?
It's just, yeah, close enough. 717. Tag her in the chat, and we'll get those questions at the end, and then we'll catch up on the weekly stuff. What's been going on in between? This is going to be kind of a long Prezi, so I'm going to try and breeze through it as quickly as I can. So, welcome Zach, welcome Shane.
Hey, how's it going, everyone?
If you gentlemen have any questions during the Prezi, feel free to interject at any time. All right, let me see here.
Well, I do love coordinate systems, Cartesian simultaneity, and my new favorite thing is to make fun of space-time as a physical abstract. So when we get there, I'll definitely have lots to say.
Nice. All right. Here we go for presentation. Can you guys see what I'm showing? Then I'll put it up on the screen share isn't enabled.
Yeah, I just clicked on it and it allowed me to make it bigger so I can see it.
Okay,
So we
cool,
just put
cool.
your center cam, and I think we're good, except you're not in presentation mode, right?
In here? In this? No.
Yeah.
I am now, though.
Right. Go.
Okay.
That's nice.
Good?
Yep.
All right, cool. Let me make sure it looks... Oh, hold on one second. I got to add my webcam scene on full screen there. There we go. All right, give me 1 second. I'll get this started, and then we're good to go.
All right. Did you guys have a good week?
Yeah, hell yeah, man. I think we had some fun bringing the celestial theodolite argument to some globers and watching them just like spin their wheels, spit fire, address different arguments, make up their own version. It was insane.
Oh,
Very,
dude,
very entertaining.
we'll definitely do a Cell Theo recap towards the end here, for sure. But, all right, I am ready to begin, gentlemen. So here we go on the history and importance of coordinate systems, reference frames, and the physical interpretation of what's being put forward with all this mathematics that they're doing, and the laws of physics and where they apply and what they're doing with them. So this reference or this presentation is mostly color coordinated throughout the slides when I'm discussing things and we're talking about what's on the slides. I want you to think about the words in a certain way. So when we're talking about abstract mathematics, for example, the coordinates will be red, noted here. When we're talking about a reference frame, when we're talking about a coordinate system that describes a place where a measurement was taking place with an instrument, I want you to think of that in blue. That's where we're going to be applying like a physical meaningfulness through the mathematical abstraction. So reference frames are describing a place where there's an observer with a measuring rod and a clock. So you can kind of, and this isn't to be confused with a human per se. This is just to be clear on place where the measurement is taking place will be what is being described. Now, relativity theory makes a specific definition of a reference frame where the phenomenon and the observer are going to be where the reference frames are defined. In Newtonian physics, you can arbitrarily define reference frames, and you could use like a fictitious midpoint to describe rotation and things like that. But for relativity theory, you're not allowed to do that because they're going to remove the idea of absoluteness, and we'll go over what that means, like philosophically, and how they built physics on the backbone of that. So time and distance in relativity theory are changed as a function of the square of your velocity over the speed of light square, and that's going to be the relative motion between the source and the observer. Now, in classic physics, time and space are absolute, and we'll get into what that means and how relativity deviated from that. So just real important to note, though, in relativity theory, the use of a fictitious frame is not valid because that would be considered like an ether frame or a preferred frame to describe things, and Einstein's theory is supposed to be physically meaningful. So moving forward, remember that all experiments have to be described in the context of where the measurement is made and where with respect to the phenomenon. Okay, so coordinate systems, right? This mathematical abstraction that I was talking about, we live in what we call over at ether cosmology coordinate system simultaneity, and it's true, meaning that all the different types of coordinate systems, so starting with cylindrical, conical, rectangular, those are all equal coordinate systems. They just need the correct corresponding transformation to get to them. And what we can show is that that applies to all kinds of different coordinate systems, not just the like two-dimensional or doing a projection, like a stereographic projection or something like that. We can do, so anyway, we'll just build on what these look like. So using this book as our reference, we're going to look at the coordinate system. So we have a standard rectangular coordinate system with our X, Y, Z axis. And then we have a cylindrical coordinate system. And we have the corresponding transformation to get back to the rectangular coordinate system here, given by r cosine psi and r sine psi. Oh, so just the angles, basically. It's just an angle transformation because all you need to have is a common axis in alignment with the coordinate systems. So as long as the z-axis is in alignment here, they share that same z-axis, you can take that these angles here and get the corresponding transformation to get back to the original coordinate system. So here we have an elliptical coordinate system, same situation. Here's our corresponding, what do you call it? Corresponding transformation, and here we're using cosine h's for hyperbolic trigonometric functions because we're using a hyperbolic curve there. So we get into spherical, we're doing the same thing, and this is how you get back to that intersecting plane there for that rectangular coordinate system. Same here for these prolate spheroidal, parabolic, so on and so forth, conical. We're not going to spend too much time on these. They're just kind of here for eye candy because I think they look cool. So anyway, like I said, all equivalent, all equally valid at any time. Coordinate system simultaneity.
So no matter what shape it is, you can put a coordinate system onto it.
Yeah, so you'll be defining it specifically with fixed coordinates, with a rigid point at the center for your XYZ axes and all that. And as long as your midpoint there aligns and you have a z-axis alignment, you can do these. Then they're all valid.
Like it's based on like your observation can be represented cylindrically or in like a different Cartesian or spherically, and any of those are valid at any same time. And when you translate between them, there's no loss of information, there's no loss of time. That's why we say it's instant, right? Because they could be fairly represented in either way, but it all because it's tied back to a real observation. That's why Cartesian simultaneity works.
Yeah.
So do you think without actually stepping far enough away to see it, we can know, like, if there is a shape at all, if there is any kind of undulation? Do you think we could notice it from taking measurements here on the ground?
No, that's not really the purpose of the relationship established with I was showing. This is for like fixed coordinate systems with a rigid defined dimensions, spatially defined dimensions. So I don't,
Okay.
yeah. So yeah, when you get into the mathematical description of how we're going to describe all of these, right? We have that mid central fixed point that's stationary, non-rotating, and then from that we can have our x, y, z, t axes that are spatially defined by whatever coordinate system, whatever we need it to be for the coordinate system to make the description. So the philosophy came about that through how they get into the mathematical derivation for how they define a reference frame and how Newton's bucket came about. There was this idea that space and time were absolute, and the way that the laws of physics and all that were derived were in the lab frame, which is the Earth, and that's where they apply. That's where they're valid. That's where you can make accurate predictions. But they want you to think of the Earth as not the inertial frame philosophically, because they all believe that the Earth is in motion. They were all Copernican lads. So when they look at the small scale for the laws of physics, they're like, okay, yeah, like for your local predictions in the lab or whatever, everything will adhere to, everything will appear as if we're in an inertial frame. But if we were to do something on the larger scale, like say send a ballistic missile, thousands of miles to a target, we would have to use a coordinate system that's fixed at the center of the Earth and non-rotating. And it's not so much about defining it at that location at the center of the Earth, because the radius value in the equation can just be subtracted out, and then it would just be relative to the surface at any point. Like all of these things that they construct and want you to think about the Earth mathematically to get you to accept the idea that like it just feels inertial, but we've got these different coordinate systems that we have to use for this different scale, because otherwise it'll be off because we're actually a non-inertial frame, etc. When the effects that are describing it can be described through other means, and everything indicates that the Earth is stationary with respect to another dynamic with other dynamic motion, meaning the sky. And then without getting into ether or anything, just kind of keeping it simple, everything would be derived with that relationship where all motion is relative to the Earth to make the prediction for the laws of physics. And then we'll get into the mathematical implications of that too as we go forward. So they had this concept of, they needed this thing to be absolute. They needed absolute time and space. They need it, but they don't want you to think of it as the Earth. So Newton philosophically said that he would put it, he's estimated that it would be in the center of the solar system, perhaps at the barycenter, which would be the gravitational equipotential point between all the other planets in the solar system and the mass of the sun. So it would be not in the center of the sun, but it would be, in their paradigm, right? It would not be in the center of the sun, but it would be like off center to it. So it exists, but they're just not sure where. And then when they get into making measurements and defining reference frames, which they're going to derive using this concept of absolute time and space, we need to know where we're going, when we talk about a reference frame versus a coordinate system, what are we talking about? Are we talking about a place where a measurement took place, or are we talking about an arbitrarily defined coordinate system where you're using a fictitious frame? So these are important things to make a distinction about. So remember, always in blue is where the measurement is being made. There's instrumentation there. There's a clock and a rod to make some sort of measurement. And whatever the clock, just to keep it simple, whatever there needs to be there to make the measurement, that's what we're talking about. And the motion is going to be yellow. So when we're talking about motion between reference frames and all of that, Um, some frames will be inertial, some will be non-inertial. Um, okay. So again, when we talk reference frame, it's not to be it's not to be confused with human observer necessarily. It's about the instrumentation making the measurement. Okay, so the Newtonian concept of absolute space here is going to be that there's a primary inertial frame that is non-rotating, it's fixed, it's stationary relative to the fixed stars. So Newton, like I said earlier, said that perhaps the barycenter or the center of the sun was stationary and non-rotating with respect to the stars that appear to be fixed in the sky because they're so far away, right? That's the interpretation. So again, the lab frame isn't the primary inertial frame; it's in the sky. So spatial measurements will be independent of motion when we use absolute space. So all units defined are going to be absolute. Like in other words, a 12-inch ruler isn't going to be a different length when you're in motion relative to somebody else that's stationary or also in motion. And the same for time. So the inertial frame is implying that even though there's uniformly a moving frame to be used, some frames are more fundamental than others, because remember, they're going to go on to define their inertial frame as a frame that's in uniform translatory motion, meaning it's just moving at a constant speed and it's not changing. And then they can use calculus to derive that there's no change in time between the observers, assuming that time is absolute for all observers. And because time is absolute for all observers and there's no change in time, they would interpret that as saying that there's no inertial forces, i.e., there's no acceleration acting on that system. So Newton's equations would hold true in that system. So they say that the Earth, is moving at a constant velocity. It's so big and it's rotating. Um, so it just like appears inertial at your local scale, but on a bigger scale, it's non-inertial. That's how they want you to think of it. And then mathematically, they can represent what a frame like that would look like to make the correct prediction for the laws of physics. And in that particular case, where Newton's equations hold true for the predictions of motion in a frame that's like, for example, when I'm saying uniform translatory motion and all that, just think of an observer in a train moving at a constant speed. He's not going to
So if
feel
there
any.
was an acceleration or deceleration, would it throw this off?
Yes, yes. And you would be in through calculus, you would be able to detect that change because acceleration is a derivative of velocity. It's a time derivative, velocity. So you will you can mathematically represent that, predict that, and show where the frame isn't inertial and where Newton's equations aren't going to apply to it. Absolutely.
Okay, so do they do that with Earth in its elliptical orbit around the sun?
Yeah, they just assume that the speed, the gradual change is so slow and gradual that it's, a constant for all intents and purposes. And then from that, you would take the relative velocity change, which is going to be zero, or, it's going to be 30 kilometers a second when they take their second measurement. And there's going to be no difference in time there when they take a time derivative from when they add the relative velocities together.
Okay.
And then so from that, they're like, okay, F equals ma here in this frame. We're not detecting any acceleration or anything like that. So that's how they get into that. So this is the backbone of of classical physics and how they came to this understanding using these assumptions and building off of this framework. And so we're seeing two parts of it, right? Like the philosophical interpretation of like some idealized space that's stationary and non-rotating, and we're going to use this for absolute units of measurement, absolute units of time, absolute what's the other thing? Oh, absolute simultaneity. And then from that, we're going to build the laws of physics, because that's what they end up doing. So continuing off of the concept of absolute space, where there's this idealized fixed non-rotating place that they're just not quite sure where it is. There's also absolute time, and what we talked about earlier being the acceleration being a time derivative of velocity. And when you when you take that derivative and you determine that there's no change in time, you would predict that Newton's equations are going to hold true. So we'll look at that on the next slide over here, so we can show what that means. But this is just kind of elucidating on what that means. So if time is absolute, that means it doesn't matter if you're moving or not. Time is going to be the same. So this is how they can make that assumption for the prediction of whether or not there's going to be forces felt in this frame when they do the comparison. So there's two concepts of absolute time and space, and one was from Newton, and the other one was from Mach, where he said that time was an abstraction due to relative motion with respect to the mass distribution of the Earth and the entire universe. And that quote, that summary that I just gave, is often misquoted, which we'll come back to. And this is super important because the competing ideas of time and space, there's only been three major proposals to it, and that's Newton's proposal, Mach's proposal, and Einstein's proposal, which deviates from absoluteness, which deviates from the absolute and makes it completely relative. And this will be extremely important when we get into how these mathematics are supposed to be the representation of reality. So that is the important takeaway here for all this as well. Yeah. Okay, so earlier when we talked about acceleration being a time derivative of velocity, what that would look like, you would have acceleration equals derivative t over the derivative of v, and that would come out to be 0, because what we would do over here on this side, what we're looking at, we have VA equals VB. So this is the velocity summation of two frames that are in relative motion to one another. It doesn't matter if their velocity is the same or if one's traveling faster than the other. The important part is we're going to add them together and get their V relative velocity, the summation of these two. And then we're going to do it again. And if there's no change in them, then that means that's constant. And if it's constant, then when we take our derivative, our time derivative of the relative velocity, it's going to come out to be 0. And from that we've determined that there's going to be no inertial forces acting on these. And here in this example, they use particles. So if you were an observer on the particle, you wouldn't be feeling any force pushing you to the back of knocking you off the particle or something like that. Okay, so I think that there's that up. So when we get into dynamics, which means future predictions of motion based on actual forces, versus kinematics, where relative motion is true and you're not concerned with describing forces or making predictions based on forces, you're just making predictions based on measurements of velocity over time. The big distinction here is dynamics is how you validate or invalidate your hypothesis on your prediction of why these forces are interacting and stuff. So when we get into how all of this is going to be applied, they started using these concepts to determine mass, length, and time. And from those units, they built all the laws of physics and units of measurement for force, momentum, and all that. And they also started applying these equations to the sky. And using an algebraic shuffling, you can interject some Newtonian constants into where Kepler's laws would be, which are just based off of empirical observation, which is just kinematics, where it can't tell you if the Earth is in motion to make their model true, or if everything is in motion around us, or if everything is in motion around the sun, which moves around us, etc. Right, so on and so forth. It's just kinematics. But when they applied the Newtonian constants for dynamics, they were asserting force and causal mechanisms, and this was hugely important to their philosophy about how they described and interpreted the cosmos and what's happening in the sky. Because the battle for cosmology in your mind really is, how do we get the equations that we have on the Earth that make measurements and show some resemblance of reality to apply to the sky in a way that we can tell you how and why the bodies in the sky move.
This is my favorite part of the history lesson. So you're saying that historically a dude named Kepler had all the empirical observations known that was predicting they moved in ellipses and could quote predict the motion or planet of anything, any of the wandering stars in the sky. He knew exactly where they would be based on empirically watching them and nothing else, right?
Yes.
And then Newton comes along and he's like, "Ooh, that's neat. You see how you can do all that and all that's perfect? Well, what if I told you why all that was happening?" And he was like, "Look over there. It's some algebraic shuffling. Dun, 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 dun. He's like, "See your equations? Well, actually, they're my equations, and they're the same, but they describe the same periodicity. See that constant? Well, bump and put in my big G value that I just inferred off some density, and boom, now I have a dynamic cause for everything. And it's really just Kepler's laws still, right? It's like a magic trick that he pulled."
Yeah, that's
Just
exactly
changing
it.
some of the definitions, right?
Just
Pretty
changing
much.
out just changing out the variables, and because it's a ratio over the constants, it's going to work out the same. So when they swap them in and out, they're not actually swapping in anything meaningful because the mass in the equation actually cancels out. So it's just based on the ratio of the constants and the periodicity, which is all Kepler had. And that's why they work out together, because it's only about the periodicity. So it's always going to scale to the ratio of the constants used. So they've got like this really neat proposal of how they can frame it. That's what we covered last week, when we went over the algebraic shuffling that they do there, and how you can cancel things out, and if the terms are the same on either side, you can reduce it down, etc. Well, when you reduce all that down, for example, for like the Newton's equations, especially when you're dealing with stuff in the solar system, the mass of the sun outweighs everything. So you could put the mass back in any equation regarding planetary motion, so-called planetary motion, or satellites on Earth, man-made, or the moon, etc. And everything is going to cancel out, and it's just going to be a ratio of the mass of the sun and the gravitational constant, big G, which is all derived off of the torque angle from Cavendish, which, if gravity was a dynamic system as they described, the old three-body problem that they've never solved, well, the positions of the planetary bodies would also affect that measurement. So they would have to take like measurements throughout the year and do differentials to zero out what Earth's gravitational potential would actually be based on the planetary alignments and their masses. If the algebraic shuffling worked out to give you the actual masses, all of this would be mathematically represented, and then they would have like differentials based off of that, where they could zero out how much of the gravitational force is coming from the Earth versus influence from the other bodies. They never
So
do
all
that.
their supercomputers that are working on the three-body problem say that we should have a different sky just about every night, if the laws of gravity applied to, the solar system as they know it.
Exactly.
Mm.
And it all started with a little calculus mixed in with a bucket full of water. So yeah, so with this mindset of being able to define a frame that's in uniform motion that can predict F equals ma, which how it's presented in the textbooks is that this is, this significant feat, and we're going to show that when you do conservation laws and other dynamic analysis, you can show that the lab frame is the only frame that actually makes the correct prediction. When mainstream, when they talk about dynamics, they say that the lab frame is just by choice of convenient coordinate systems with respect to some other preferred frame, which is either the fixed stars or the barycenter. So if you've ever talked to someone about a gyroscope and you've said, "How does a gyroscope maintain its rigidity?" And they say, "Well, with respect to the fixed stars." Right? Simple enough. Well, no one's ever been to the fixed stars to confirm that. We've only ever this started in the lab frame. It's only ever been in the lab frame. This only applies in the lab frame. So to be like, "Hey, you know where this is with respect to the sky," makes no sense, but it's the philosophical bias, and we're going to see how that kind of ruins things moving forward. So in dynamics, only the lab frame will make the correct prediction for all future predictions of motion and conservation laws and energy predictions. When using, it's not by choice of convenience. That's just an old wives' tale, as they say. Now, earlier I mentioned that using absolutes for length and time and force, asserting that mass and force are equivalent through F equals ma, um, or that they're interchangeable. They build the laws of physics off of this with length, time, force, mass, velocity, acceleration, energy, work in a system, angular momentum, velocity, inertia, or moment of inertia, linear momentum, angular momentum, linear impulse, and angular impulse. So they've got all these different relationships that hold true that we can make measurements with, that seem to comport to reality. We can do things like do mass addition. We can have 5 pounds. We could add 15 pounds to it, and now we have 20 pounds. Like all of these things, when we apply all this, all check out. When we take these equations and apply these out, everything starts to work out. So a quick note on mass before we continue is that it's a circular definition is given for it because it's defined as a quantity of matter, which is calculated by the product volume of density and volume. I think I said product volume by the product of volume and density. If we look over here to the left, we see to find density, we need density equals mass over volume. And to find mass, we need density times volume. And to find volume, we need we need mass over density. So we have this circular quantity definition that we could tell you what the value, what the numerical value is, but we can't tell you what mass is in terms of what it is. And this has been kind of like a philosophical thing that's been that we'll reference back later that ends up haunting Einstein. And so it's just kind of like a circular thing with no operational definition, but it can be mathematically derived through this. So, and then in relativity theory, mass changes as a function of your velocity or energy. So the faster you're moving, the more energy you have, which means the more mass you're going to have. So you're going to have relative mass. You're going to have a change. You're going to have relative time, relative length, and relative mass in relativity theory. So a quick recap on this before we move forward is that there's a preferred frame. We've got these awesome laws of physics. We're making predictions of motion. We figured out relationships of angular momentum. We're making great strides here. We're applying our equations to the sky. We're telling everybody how much Jupiter weighs because of its periodicity and how long it takes to complete an orbit around the sun, which is obviously based off of its mass and gravitational potential relationship with respect to the sun. So they've got this whole thing going. So what went wrong? What went wrong? Well, before we get to what went wrong, we have to look at this reference frame situation because we're going to make measurements against it. We're going to start to in the 1800s, we realized that we can make measurements against this absolute frame using light. We can measure velocity with light using the fringe difference. So before we get to the need to deviate from this absolute framework, we're going to cover why it was necessary in the first place. So earlier, I touched on predictions of motion and reference frames and where these equations apply. If you're in an inertial frame, as defined as being in uniform motion at a constant speed, or if you're in an acceleration, which would be a non-inertial frame. So in Newton's time, one second here, I'm going to get some water. In Newton's time, he spun a bucket of water around, and he spun the bucket. So he applied his equation for centripetal force to the bucket, which is Fc equals m times velocity squared over r. And the velocity is just how fast he spun the bucket. Mass would be the mass of the bucket full of water. And that's going to tell you how much the water is going to curve in that hyperbola. And when he applies that equation, it predicted how much it curved. So it was correct. It was good. So when you make the prediction of motion with respect to the lab frame, meaning the bucket is in rotation with respect to the lab, you correctly predict that there's going to be a bend in the water. But suppose you put a little lad inside of the bucket, a little bucket lad, or a bucketeer, as Cassander calls him. And in his frame, he's going to be stationary. He predicts the bucket velocity is 0, but he sees the lab frame and Newton, who's spinning him, moving clockwise And so he predicts in the bucket frame that his velocity is 0, and he predicts that there's going to be no force on the water then. So when you do the centripetal equation, mass times velocity squared over r, with 0 velocity, you're going to get 0 force. So he makes the incorrect prediction. So if you're in a non-inertial frame, if you're in rotation with respect to the lab frame, the laws of physics are not going to be applicable to you. So in this case, we're using an acceleration, but we're also, or in particular, a rotation acceleration. So we're going to go over the linear variance of this, and also for the for uniform transitory motion, which is their big claim to success in how they interpret cosmology and merge their concept of mathematics with an Earth that's in motion versus being actually stationary. All right. So lab frame, correct prediction. Bucket frame, the frame that's in motion. Remember the color notes. So when we get to purple, that's going to be forces. So FC is going to be our centripetal force. Mass in Newtonian physics, these are interchangeable here. So mass is going to be, because like to get this to move, like for example, its moment of inertia is going to be mass times acceleration. So the way that they're equating all of this through that is that relationship. So this is why these are purple. So anyway, when we're looking at that, that's how I want you to think of that. So lab frame incorrect, or lab frame correct prediction, bucket frame incorrect prediction. He predicts the water will be flat, but it's curved. So in the same analysis, when we apply it to a driver who's accelerating with respect to a hitchhiker, we can do the prediction of the hitchhiker frame who sees the driver accelerating towards him. He applies the mass of the driver times the acceleration, predicts the force that the driver is going to feel. That force you feel pulling you back to the seat as you accelerate. That is going to be what is felt there. So he makes the correct prediction. So when we get to the hiker is not moving with respect to the lab frame. So he predicts that he will have no force will be acting on him. He's not going to feel any acceleration, no inertial forces. So he predicts his will be 0. So he makes the correct prediction. When we do the same analysis with the driver and the driver frame, he predicts that based on his velocity, he looks at his speedometer. He goes, okay, with this is my mass, this is my velocity. I feel this acceleration, correct prediction, great. When he looks at the reference frame of the hitchhiker, well, when you do the analysis, the driver becomes stationary and you have to make the hitchhiker move towards you. So the driver predicts that there is a force accelerating the hitchhiker towards him as the driver remains stationary. And that's not what that's not what the hitchhiker feels at all. That is the incorrect prediction. The driver is going to drive right past him and the hitchhiker is going to feel nothing. He might feel the wind or something of the driver passing him by, but it's not the force that we're talking about here. That would be like a Bernoulli's principle situation with the translation of the air. But yeah, so incorrect prediction there. So it's not the correct force. And if you have to introduce fictitious forces to make the frames equivalent, then you are doing fake physics. The frames are not equivalent. This is the important distinction. I actually had someone, a physicist, come and comment on a video I did last night talking about, but if I introduce fictitious forces, the frames are equivalent. We learned this in 8th grade. It's like, yeah, dude, the point is that you have to introduce this fictitious force to make this guy move to you, but we know he's not moving to you. It's not valid to do this. So you can certainly do that, right? But that's not a valid application of it. You're forcing the equivalence there's no measurable force on this lad. So if you make it equivalent in that way, it doesn't mean anything. So we can do the same thing with respect to a pendulum swinging. The pendulum swings back and forth as a function of its mass and height off the Earth. If we do the reverse frame where we have the Earth do the swinging for the pendulum would be swung off into space, or it would be flung off the Earth, however you want to conceptualize it. because you're using the mass of the Earth to do the work instead of the mass of the pendulum ball. So again, with the motion with respect to the pendulum ball is the only valid frame. And we will get an analysis for a Foucault pendulum. This is actually an analysis for a Galilean pendulum that's just going back and forth. Thank you for the correction on that, Franco. Much appreciated. So there will be one for rotation as well. But this is for the linear variant of just moving back and forth. So we're showing here, though, that the same application applies, though. It would predict that the energy of the ball would, it would be astronomical how much energy would be put into that. So they're not equivalent. They're not. All right. So now we have dynamic analysis of Bennett's train. So this is a great example of the uniform translatory motion frame that I was talking about earlier. This is how they want us to think of the Earth. We're in this closed system due to the gravitational field. We're moving at a uniform constant speed. So therefore, we're not going to feel any inertial forces acting on us at the local scale, and et cetera, right? Only when we get to the big scale, we're going to have to use the center of the Earth. And then when we get to the big scale, we're going to have to use the barycenter, which is all based off of geocentric observations. So the reason that makes the correct prediction, just by the way, a little FYI for the boys, the reason that the barycenter makes the correct prediction is because it's derived from geocentric observations. So it's all just based off of positions. It's not like the gravitational potential wise situation, like they want you to think about it. The relationship and the accuracy of it is based off of positions of the planetary bodies. So, which is viewed from a geocentric perspective in the way that they do the alignment. So, all right. Anyway, what we have here for the train scenario is if you have an observer inside the train and he's juggling balls, he's not going to move out from underneath the balls. If he puts the balls on the ground, they're not going to roll out from underneath him, right? They're not going to roll to the back of the train. If the train were accelerating, they would do these things, but he's moving at a constant speed. So there's not going to be a change here. So F equals ma applies in this frame, and it predicts that there's not going to be any inertial forces felt. So this is that mathematical relationship between how they derived using calculus and the relative velocity change using velocity composition, meaning just adding the velocities together and then seeing if there's a change when they add them again at a later point in time, and then taking a differential of that change in time or change in velocity. And if there's no change, then there's no change in time. And if there's no change in time, then there's no inertial forces acting on them. So once they've got all that, but we're going to show here that that's not even valid either. Even though it makes the correct prediction in a certain circumstance, it doesn't make the correct energy prediction for the balls because it doesn't incorporate the energy potential of the horizontal component of the velocity of the train. So when you go through the equation for the prediction of energy of the balls with energy with respect to the lab frame, so the motion of the balls and the train is with respect to the lab frame. You have the balls and the train's velocity, horizontal and vertical, with respect to the mass of the balls and the height that you're throwing them and the gravitational acceleration. And that's going to make the correct prediction for the energy output. When you do it with respect to the observer in the train, he's not aware of the train's velocity, so he only has the energy prediction for the vertical component of the balls, and he makes the incorrect prediction there. So with that, it's like, isn't it more complicated than that? That's it. That's all it takes, guys, to show that the frames are not equivalent. And I don't know, like I put a clip on my channel. You can check it out on Space Audits. It's one of the recent clips with Bennett from Flat Earth Fridays, episode 106, I think it is. If you go to that and listen to that convo play out, it's like, it's so simple, you almost overlook it. And then when you hear it play out with somebody conversationally, it's just like, oh yeah, that's super obvious. It's been there the whole time. So this concept of an inertial frame being defined by Newtonian and Einsteinian philosophy as arbitrary or in uniform transitory motion is invalid. The Earth is the inertial frame. The lab frame is defined as needs to be redefined as fixed, stationary, and non-rotating and absolute. So this choice of this convenience thing it's a myth. You can do the same analysis with a biker on a ramp. Is the Earth moving up towards the biker to cause the motion of the biker as he goes down the ramp? Well, that would give you a prediction where he would, fly off the Earth. He would be going so fast. If you do the mass of the biker going down with respect to the stationary Earth, you make the correct prediction. So, but wait a minute here. Aren't we flat earthers? How are we using the mass of the Earth? Aren't we doing globe science? Nope, we're just doing regular old physics, and physics is based on constants and ratios. And for certain instances, you need constants. Well, actually, for everything, because everything you're going to be measuring is a deviation from that. So, for the mass of the Earth, right, we've got this nice story about Cavendish and his lead balls and the torque angle deviation, which comes out to be the gravitational potential of the Earth with respect to the mass of the Earth and the mass of the balls. So you can backwards derive what the mass of the Earth would be in that. So they have this nice calculated value, even though the density, when they try to work all that out, is off, and they had to invent a molten iron core to make up the difference for what they predicted. Forget about all that stuff. All we need to know is that we have a constant that we need to use. So for any experiment we're doing as flat earthers, or however we want to conceptualize it, you could just take the area that the experiment is being done in and then just say, okay, this area of ground would weigh, let's say 10,000 pounds. Just whatever it is, it just has to be more than what the experiment is that you're doing. So when you do an analysis for predictions, you can show which frames are invalid and not invalid. It just makes it easier to just reuse their constant. So I didn't bother like redefining, any of that, but just like how to think of it and understand what's being put forward and what they're doing. They have measurements that they use as a constant. And then from that constant, they can establish other ratios with it, but they need the constant to start the process. Whether or not the constant is physically meaningful or not doesn't necessarily matter, because what we're going to show when they went to take experimental measurements of the resulted force of this mass and force equivalence and all this, they didn't get the velocity measurement that they needed to when they used light, and they had to redefine all the physics over that. But yet, this relationship shows it still holds the invalidity of the situation. So it doesn't matter about the mass necessarily. It just has to be, we just have to have something to have it be in reference to. So I hope that clears that up. All right. So if you're trying to satisfy conservation laws and make the predictions of energy potential or energy output in a system in regards to the reference frame analysis, then just pick a constant and just know what it is rather than interpreting it as what they want us to look at it. Like where they essentially want us to think like we weighed the Earth and then using our relationship with the periodicity of the motion of the bodies in the sky, we weighed the bodies in the sky. It's like that's insane. But
Absurd.
but the relationship works because they've got constants to start with. Now they were proven invalid and they didn't give those up, so that's the big distinction there. But you can still use them for other purposes as long as you know what you're using them for, right? Math is a tool, and if you don't know how to use the tool, you're just going to hurt yourself. That's a quote from Shane St. Pierre regarding maps. Maps are a tool. Math is a tool. All right, so we're going to cover Mach's analysis of absolute space real quick before we move on, because this is often misquoted in the mainstream, and it's super important to the concepts philosophically. So he talks about Newton's bucket, and he says, Newton's experiment with the rotating vessel of water simply informs us that the relative rotation of the water with respect to the sides of the vessel produced no noticeable centrifugal forces. but that such forces are produced by its relative rotation with respect to the mass of the Earth and the other celestial bodies. So Mach was half right here, but in the mainstream and in textbooks, they always cut out the mass of the Earth part, and they just want the mass of the celestial bodies for it to be part of that. Because when they later on, when they go to remove the concept of an absolute frame, they still need something for it to be relative to. So Mach's concept was that the mass distribution of the universe would impose inertial forces on us, and if you were stationary and if that universe was in rotation, the forces imposed on you would have the same effect as if you were the one that was in rotation with respect to a stationary universe. So because they argued that there couldn't be an equivalence there, and then it was shown mathematically a couple years later by Max von Laue that using I think that they call it the rotating, not rotating, is it rotating cylinder, rotating shell, the rotating shell that they talk about. That's like the mathematical description of how it would play out, and it shows that. So, like, in the big point of contention was that the Earth couldn't be oblate if if it wasn't due to the rotation of the Earth itself. And Mach was like, no, it would be oblate if the universe was rotating around it because the same forces would be imposed on us. It could because it would and they would be equivalent in that regard. So that was how he conceptualized it. And so instead of having absolute space in the solar system, it was with respect to the universe, the mass distribution of the universe specifically. All right, so half right on that. So when they went to go and test this in 1887 with Michelson-Morley, when they knew that they could take absolute measurements of velocity using the ratio of the speeds in question that they were trying to measure, the path length of light that had to travel in the apparatus to make the measurement, and over the speed of light, which would give them the prediction for how much the speed would change. And with that speed change, you can predict how much phase difference there would be, meaning how much fringe pattern there's going to be. So when the light beam is split and it goes clockwise and counterclockwise to itself and it's recombined, it'll either be in phase or out of phase. Relativity theory predicts that when the beam is split north, south, and east, west, that when it recombines, there'll be no phase difference in either direction. But what they measured was that there was a phase difference in the east-west directions, but it wasn't to the magnitude that they had predicted for 30 kilometers a second, because the way that their math and ratios all work out is that the velocity would be mandatory of 30 kilometers a second. So anything less than that completely falsifies all of their mathematics and ratios that they've been applying to the sky and how they've been, telling everyone that how everything works, essentially. Because they've got a really accurate system on the ground that makes measurements. They've got accurate ways to describe things with momentum, mass, weight, angular momentum, velocity, acceleration, where the laws of physics apply, etc. They've got all these great predictions, but they also applied them to the sky and made their cosmology a part of physics. And when they went to take measurements of that to confirm it, they were not even close. So the air tolerance of this apparatus was 2 kilometers a second. They measured a fringe pattern. Oh, I'm sorry. Let me back up a little bit on the fringe. So when the waves recombine on the interferometer, they're either going to be in phase or out of phase, which is going to create constructive or destructive interference, which means if it's constructive, there's going to be a bright patch, and if it's destructive, there's going to be a dark patch. And you could measure that dark patch in units of wavelengths of the original wavelength that you used for your laser beam or whatever you're using. They didn't have lasers in 1887. They used incandescent lamps, but the wavelength for incandescent light had been measured, so they knew what the wavelength would be. But anyway, when you take that wavelength and you measure out that dark displacement gap, the square of that distance is proportional to the velocity in question. So they have a direct relationship there. So they knew exactly how much would need to be changed if they were moving at 30 kilometers a second. And when they measured 6 to 8 kilometers a second, they basically refuted their entire cosmology and physics as they were applying it to the sky. All of their dynamic predictions meant nothing because this velocity has to correspond to it. So how did they answer this? Well, they had to round the measurement down to 0 and say that this 6 kilometer a second measurement was actually 0 kilometers a second. And then from that, they can say that the reason that it was 0 kilometers a second is because of link contraction and time dilation as a function of moving through static ether. So this was Lorentz's theory and framework that he proposed, and he's using the Lorentz transformation here, which shows that the time coordinate and the distant coordinate are going to change as a function of the square of the velocity over c squared. So in other words, it's going to be a little tiny amount. Now, what they measured was way bigger than the little tiny amount that they're predicting. So keep that in mind. That to make this whole thing work, they have to ignore this comparatively massive measurement and say that what they actually measured was nothing because of a contraction amount that is wildly insignificant in terms of scale to the original measurement. Pretty fascinating stuff. And with that comes an entire deviation from classical physics in terms of how we derived everything with absolutes. So we'll take a look at what that means and what they had to jump into philosophically to answer this. Because what they proved is that the lab frame is stationary. The velocity of the lab frame is 0. And my explanation of this personally would be that the measurement of velocity is with respect to a dynamic ether that is being translated from the motion of the sky, because later all of these measurements will be reproduced and shown to show a sidereal fluctuation throughout the day, where the speed of light changes throughout the day, meaning it's faster and slower throughout the day, and it corresponds to sidereal time and also the positions of the sun throughout the year, specifically the equinoxes, where it's the fastest and slowest on those days. Very cool stuff. But they don't have the velocity component that corresponds to heliocentrism. So they have to ignore the sidereal fluctuations. They have to ignore the velocity. They have to ignore all of that. They have to ignore that the displacement is proportional to the square of the velocity. They have to go against established science that they had already figured out from Fresnel drag in 1852 and moving on. By the time they got to 1857, they had the exact derivation for how to make the prediction for the velocity measurement. And this is actually the same equation that they use for Sagnac. So 2 times the distance times the velocity over the speed of light. Well, you replace this distance with area and this velocity with omega for angular rotation. Well, this describes the same thing, but they don't, and they only want you to look at the minimum and maximum peaks of the angular rotation rate instead of the square relationship of the actual fringes themselves. They only want you to think that you can measure rotation in degrees and not the translational speed. You can. It's just they don't want you to know that. Okay, so Einstein comes forward. He goes, all right, it's logically inconsistent to say that there's an ether framework, there's a preferred frame, but we can't measure it because we're contracting in it. That doesn't make any sense. That's very ad hoc. Let me try another ad hoc solution where we're going to say that the reason we didn't measure it is because there's no preferred frame, there's no ether, but instead of having link contraction as a function of the ether as the mechanism, we're just going to say time and space contract as a function of velocity itself, instead of as a
And do you
function of
think that might
relative
be
velocity to the ether.
one of the most crazy things that people just decided to accept I've ever heard? Like, that is a BS excuse if you've ever heard one. Like, oh, it just
Well,
shrunk a little bit. You
which
can't
is,
measure it. You can't see it. It's like magic. And actual physicists were like, yeah, okay, I'll give them that.
Yeah,
It's insane.
The only thing they could do to answer this, because they already got in a pickle with Aries failure, right? They were already in a predicament. Now, because the measurement is really small in Aries failure, and they could interpret that as like a null because the displacement was only 0.8 arc seconds, which would total out to 1.6 arc seconds over the course of a year, which is really small. So they could go, maybe it was nothing or whatever, right? But with that interpretation, they had to come up with reference frame transformations using Lorentz's theory, which is the same as Einstein's theory, but he just has to the difference here though is that Einstein has to remove the concept of an ether where the motion isn't going to be relative to the ether itself, it's going to be just relative to velocity. So he just
Right.
removes like the compression mechanism as like a physical aspect of moving through ether because like honestly it's super ad hoc and what he's doing is ad hoc too, but it makes more logical sense to say that there's nothing and that it's all relative, and then to fully commit on the back of that makes more sense, if you're gonna look at
Well,
it that way.
if you're trying to understand it, right, like you have to be like you have to infuse yourself with the appropriate amount of desperation that was in the scientific community at this time to try and explain the motion, lack of non-motion that they definitely knew was there, but nobody could ever measure, right? And that's what really birthed Einstein. They were like, get up there and do it, get up there, do it, do your thing. Come on, we need it, right? So that's why it has to
Dude,
be abstract, nothing
dude,
with coordinate systems and
thi
nonsense math.
think about this. Other professional physicists already derived this, Fitzgerald and Lorentz, Poincare. The actual Lorentz transformation is just the Voigt
Doppler,
transformation
isn't it?
instead.
Oh.
Yeah, which is the Doppler frequency, which is based off of the timing and spacing of waves based off of an elastic medium. So like this whole framework is literally built on the backbone of ether, and Einstein's just going to come along and go, well, same framework, no ether, just relative velocity, and we could still use the framework, even though, dude. So get this: in Lorentz's, you can do a summation of the reference frames that you do in a Lorentz transformation. So, like when they get to like the Einstein train thing, you can do a summation of the frames, and you can determine the order of events for the simultaneous event, which we're going to cover here in a little bit. But and you can determine the proper who saw the event first, right? Now because the framework is the same mathematically, Einstein just has to say like, hey, don't do that, just don't do it. Don't determine the proper sequence of events, because the way that he interprets relative or simultaneity is that it's relative, and that it has, which would have to lead to two separate outcomes, and you can only do that uh if you don't do a summation of the things and show the proper sequence, because then all the frames would agree. And if all the frames agree, then you're doing absolute simultaneity, which is based off of an ether frame. And we're not doing ether in relativity theory. Remember, we're moving on from that because we tried to measure our velocity, couldn't do it. So we need to abandon the previous philosophy that we just learned about. All that work we spent learning about absolutes and how it made units of measurement and derived all physics. Yeah, we're abandoning that, boys. We're throwing that out.
We're done with that.
Yeah, that's over now. That's over now. So here's the reinterpretation here laid out on the first page. In fact, where Einstein says that the laws of equation, or that the laws of Newton will hold good in the same frames that his equations will hold. So he wants to apply Lorentz transformations to any frame that's in uniform translatory motion. So if you're in constant motion at a fixed velocity, his equations will apply to you. So, and then he raises that conjecture to a postulate, which is just another way of saying I'm double extraing my conjecture, because raising it from a conjecture to a postulate doesn't, it's, Anyway, so he declares this a postulate of his theory, and then he builds another postulate on the back of that, which is irreconcilable from the first, and that is that the light will always be propagated in empty space at a definite velocity, which is defined by c, and that's going to be independent of the state of motion of the emitting body or the observer. Now, it doesn't say observer here at the end of the sentence. There's a period after emitting body, but you should know that this whole theory, as you continue to read through this paper, is about the phenomenon and the place where the measurement is being taken. The word observation appears like 20, 40, or like 20 times in this paper. And all the examples given are about this is where this clock is, this is where this clock is. Now they're in relative motion to one another, and this happened. It's not this clock and this clock, and they were in relative motion to the ether or to this reference frame or that reference frame where there's nothing or whatever. They're in it's to each other. Okay, so if you're in an inertial frame as defined by Einstein and Newton, then you will measure the speed of light being constant, and you can't measure a timing difference in the speed. So when we go back to this measurement that they're trying to explain, Einstein's like, look, if you're moving at a constant speed, you're not going to get the measurement predicted by the dotted line, right? You're not going to get the 30 kilometer. You're not going to get this 6 kilometer to 8 kilometer represented by the actual measurement, the solid line. You're going to get a 0. We're going to call this the error margin here, and then just say that this actually represents 0. You can't measure linear motion. And then he goes on to say that the introduction of a luminiferous ether will prove superfluous, inasmuch as the view here to be developed will not require an absolute stationary space provided with special properties, nor will it assign velocity vectors to a point in empty space where electromagnetic processes take place. Hugely significant, because to explain this, we're not going to take the reference frame of the center of the Earth or at the center of Mars or something like that to explain this, or at the center of we're not going to invoke a fictitious frame. We're not going to use a cylindrical coordinate system overlaying the system of the relative motion between the Earth and the sun and use an arbitrary midpoint to find between them or anything like that, right? It's going to be between the Earth and the sun. And then in terms of the luminiferous ether, that would be their conceptualization of the physical medium. If you're in a medium, all motion is going to be relative to it as well. So he removes it as a fluid medium, as a physical mechanism, as a real concept, and he also removes it as a mathematical concept here with the absolute stationary properties or special properties and assigning velocity vectors to points where the processes once took place, because that would be using absolute time and absolute space, and he's proposing that doesn't exist and everything's relative. And you can answer it through his equations here, giving this transformation. So he goes on to explain, like this caused a big rift in physics. Everyone was like, "This is really confusing. What do you mean? Do you mean that actually the apparatus contracted, or do you mean like philosophically, hypothetically, kinematically it contracted? Like, what are you talking about?" Einstein steps in 1911, and he's like, "No. Dynamically, it contracted." In reality, and you could measure it if you had like some third-party stationary observer that could observe the relative motion between you and the analysis that you're doing, and it would measure that the ruler of the moving observer is less than the stationary observer, is what he goes on to say. And this is logically consistent with the idea that there's no absolute time, space, or relativity. Because if any of those things were absolute, then you can't have relative lengths, you can't have relative times that are reference frame dependent. It would be independent of the reference frames, and it would be absolute. So it would be contradictory to have an interpretation where this isn't where the contractions aren't physically meaningful. Now, Einstein goes on to say in his paper from 1905 about simultaneity, which is going to be extremely relevant in how paradoxes are resolved in the theory and how they, and how it's based on a paradox, essentially. But he goes on to talk about how he defines time in simultaneity, meaning if a spatially separated event occurs at the same time, you're in relative motion to someone else who's stationary or not, they will perceive the event as simultaneous, and you being in relative motion to them will not. So the example Einstein gives later will be a train and a stationary observer, and lightning strikes at either end of the train. But what he's talking about here is that if all the frames are equally valid, so must the sequence of events be valid. So the apparent effect, like the Doppler shift, the apparent effect that the event wasn't simultaneous in the moving frame isn't it's an apparent effect. But Einstein's arguing here, based on frame validity, that the sequence of events, and because it's a spatially separated event, meaning it's not connected to you on the train, the observer, because it's not connected to you, that it's okay that it leads to physically different outcomes based on your relative motion without violating causality, which is crazy, but it's the logical conclusion that has to be taken. Otherwise, if both reference frames agree and you have to make the sequence of events as perceived by the moving frame agree with the stationary frame, then you're conceding that the stationary frame has the preferred interpretation of events that agrees with reality because the simultaneous event actually occurred. So you see the problem there if you try to say that both observers agree on the simultaneous event and that it's just an apparent effect. It has to be a physically real effect that will lead to physically different outcomes in different scenarios that we'll go over moving forward. All right, so a big part of relativity of simultaneity is the reciprocity between reference frames. So Einstein notes here that the consequences that these two consequences, which hold mutatis mutandis, which just means vice versa, for every system of reference, form the physical content free from convention of the Lorentz transformation. So what he's saying is that when you apply the Lorentz transformation to this frame, you need to be able to show that, well, actually, this was in regards to the reciprocity for the twin paradox, but the outcome for the thing also applies to. But like, for example, say you have a stationary atomic clock and a moving atomic clock, and you put the atomic clock on a special airplane that doesn't need to refuel, and it goes around the world in a circle or around the globe and on the other side, however you want to conceptualize it. It goes all the way around, completes the circuit, comes back. When it comes back to that stationary clock, it'll be out of sync as a function of its velocity. Now, Einstein would say that this is time dilation, right? The clock dilated with respect to the stationary clock. Now, what has to be shown mutatis mutandis is that that time dilation has to be shown in the stationary clock. So if we're doing a Lorentz transformation between the stationary and moving clock, we have to be able to show that the stationary clock received the desynchronization due to the velocity component that the moving clock received or had. And then we have to give the stationary measurements to the moving clock. Otherwise, they're not symmetrical. The whole mathematical framework is based on symmetry between space and time. That's why they call it space-time symmetry, why they're merged together. Because when you transform them together, unless you're doing an asymmetrical transformation, which is an invalid use of the theory, which we will cover later here as we continue. But yeah, what we have established here is that reciprocity is key. So how we're going to interpret Einstein's example for the train embankment and lightning strikes is as follows. This is the example here, which I'll give on the next slide so we can have the visual. But the important takeaway here is that the events which are simultaneous with reference to the embankment are not simultaneous with respect to the train and vice versa. So the perceived sequence of events, because if you're moving towards it, you're going to perceive one of the things happening first. So you're not going to have the same perception as someone who's stationary, who's going to see them at the same time. The only way that you could transform them and have different outcomes is if you have reciprocity between the frames and if they don't lead to the same outcome. If you account for the timing difference and transform them and say that both frames agree on the outcome, then you are misinterpreting relativity theory. They have to be different. So here in the example, we got the stationary observer, we have the moving observer on the train, and they're moving between, the train is moving between two trees that are equidistant from one another. So we have a nice symmetrical midpoint for everything by just complete happenstance. And then we have a simultaneous lightning strike at points A and B. The moving observer on the train sees perceives the lightning strike B happening first, and he's going to interpret this order of events was not simultaneous, this A and B lightning strike. The stationary observer C here will get the information at the midpoint at the same time, and he's going to interpret that it was symmetrical. So if you came up with a scenario where a bomb would be detonated based off of a simultaneous event, irrespective of when the information is received, just based off of the simultaneous event itself. So in reality, we have a marker point for the event, so that we know that the event was simultaneous. The outcome will be that the train will explode for the stationary observer, and for the moving observer, where the event was perceived as non-simultaneous, the train will not detonate. The bomb will not go off. So this is what I meant by two physically divergent outcomes as a result of relativity of simultaneity, as a result of the Lorentz transformations. Because as a consequence of the constant speed of light, this is what where you have to take it for its maximum conclusion to have reciprocity in the transformation for the simultaneous events, while still claiming that the frames are equally valid. Because if this is an apparent effect due to motion, then you can tell whether or not who's stationary and not. But they have to be equivalent. So that's the big factor there that people overlook and don't want to accept or acknowledge when you confront a relativist, because it's illogical. It makes no sense. No one's ever seen this before. Why would you draw that conclusion? Surely it must be about accounting for the timing difference and making both frames agree on the simultaneous event. Nah. That ain't it. Einstein goes on to say in the 40s that his theory can be summarized in one sentence. All the laws of physics must be so conditioned that they are covariant with respect to Lorentz transformations. And covariant just means that the laws of physics, whatever physical quantities and values that they're using or constants, when they transform them to a different reference frame, that their values remain the same. And that they remain the same with respect to the Lorentz transformation. So using this specific transform here, I'll show you on another slide where it looks a little cleaner. Right here, in this midpoint here, this T, using this transformation, T, X, Y, Z, this is what is going to dictate how we're going to describe the laws of physics in the frame that's in uniform relative motion, because there's no simultaneity and there's no absolute length or time. And right after he says that about the transformation, he says, from this it follows that the simultaneity of two distant events is not an invariant concept, and the dimension of rigid bodies with the speed of moving clocks, and the dimensions of moving bodies and the speed of clocks depends on their state of motion. So simultaneous events are not an invariant concept. Now, if it was an invariant concept, it would mean that it remains the same under transformation. So if we took this simultaneous, because all that's different here, like the real trick to this, guys, is that right here at the bottom of this on Einstein's page 1905, when we were talking about how he defines simultaneity as where the event, or like where the watch is at, and that time is independent of the time of the simultaneous event. They're not connected. So there's no contradiction in perceived order of events. He says, we shall not here discuss the inexactitude which lurks in the concept of simultaneity of two events at approximately the same place, which can only be removed by abstraction. Okay, so it can only be removed by abstraction. He never shows the abstraction. He never shows like the follow through or whatever. But he gives this example that I laid out earlier, the same thing here in the 1920s. And then from this, he's saying that from this thought experiment, he's saying that distant events are not invariant under transformation. I'm sorry, simultaneous events are not invariant under transformation. The same applies to at any distance. It doesn't matter. This is just uncomfortably close because it makes it really obvious. When you think of a distance like, oh, it's so far away that the speed of light would have to travel for a year, like something like that. No. You know, it's hard to conceptualize. This makes it super easy, immediate understanding, and this is why it doesn't get acknowledged properly, because it's illogical to come to this conclusion. It would be like saying that if we drop these two balls at the same time, based off of releasing this platform that's holding them up, so that we know that they drop at the same time, that if an observer and they hit a balance beam, they're going to hit the balance beam at the same time, and they're just going to bounce up and down until they lose their energy, and then they're going to just remain stationary on the balance beam. That would be like saying that if we introduce a moving observer to this system, that the moving observer is going to see the B ball hit the B1 side first, and that's going to cause a deviation in the platform, and it's going to cause the balls to, bounce all over the place. And if we had dominoes or something like that stacked on the floor, the balls would hit the dominoes, and then the dominoes would, knock over one another and follow a train of events that would, start another series of events, right? And so the stationary observer would see the balls hit at the same time, and this guy would have a divergent physical outcome where the balls go in different directions. They hit dominoes that, there's different physical outcomes to as a consequence of the validity of the sequence of events in the frames if there's an equivalence between the two frames. So Einstein was actually, although this is extremely illogical, was like acting in honor, trying to put forward like the logical conclusion of the illogical framework. But yeah, then he says once it was shown that simultaneity was relative and depended on the frame of reference, every possibility of retaining action at a distance within the foundations of physics disappeared, since that concept was presupposed an absolute character of simultaneity in space and time. And how was it shown again? What was the experimental evidence of relativity of simultaneity of whence it was shown? It was a thought experiment that can't be even addressed properly because it's so obvious that it's that. So like in the bomb scenario, if you said, would you, if you were a relativist, would you be on the train with the bomb because the bomb wouldn't go off into your frame and you would live a physically different life that's divergent from the outcome where this dude sees you die because the bomb goes off?
No,
Nobody would get on the train,
I'm
but they
not
all,
playing that game.
but they all have to like make you. They all would want you to think that they would get on the train. But some of them, like I've only heard one relativist say with his chest that he would get on the train. Not only would he get on the train, he'd put his family on it. So shout out to that guy. But everyone else argues that accounting for the timing difference will rectify this, but it doesn't. And even Lorentz wrote Einstein in the 30s and was like, "Hey, do you think that there's a universal spirit that mediates that permeates the entire systems in which we're analyzing all motion and stuff, that preserves the sequence of events for causality? Because if you do a summation of my transformation, like, we can always determine the simultaneity of an event and who perceived it correctly." And Einstein never wrote him back. And the universal spirit would be like, he's kind of proposed, like, he's like, do you think there's God that's like watching all the simultaneous events that are going on? And he's like correcting the consciousness so that everything, maintains order accordingly. Einstein never wrote him back because their frameworks are the same. He just has to like philosophically disagree. Like you can't, if it's in the math and their argument is that the math is physically meaningful, then you just have to have people not use that part of the math. So there's no answer to this other than just ignoring it and hoping that nobody brings it up, 100 years later or whatever. So even in
telling though, isn't it?
Sorry, what's that? Go ahead.
Kind of telling though, isn't it?
Yeah, kind of telling. I mean,
But he
Lorentz
just
was one of the
didn't wanna
greatest
answer it
physicists.
at all.
One of the greatest physicists in the time. Someone that's your friend, your mentor, your buddy, is writing you this deep philosophical implication about your theory that's based on his framework too, right? And you just straight ghost him.
Yeah, it's not like us reaching out to Neil deGrasse Tyson. This is different.
Right.
That's crazy to just
Right.
be like, damn, whatever.
Pretty wild. And so even in modern times, like in 2002, a study was done on students at different levels of academia, so postgrads, undergrads, freshmen's, just different levels of college and different levels of physics. They did the study on the interpretation and solutions to different relativistic problems, and they all did the math right, but they had the wrong physical interpretation of what they had just calculated. And so they go on to say that we found that the students often leave the standard introductory course or advanced undergrad courses on relativity with some fundamentally incorrect beliefs about the definition of time of an event and the construction of a reference frame. So a big thing that I've been battling and why I put this prez together is because the modern relativists will say that you can define any frame arbitrarily, and like they're all hinging it based off of the Newtonian concepts, which is based on an absolute framework, which Einstein's explicitly saying this isn't what we're doing. And so when you try to get into like how do we falsify this theory, and you start to present different measurements and experiments, they'll invoke invalid reference frames to do the analysis and act like the theory is holding true and predicts it. So to show people the contradictions, it's really important to like learn the philosophical background and backbone of what they're doing, and that's why this is important. So, and this is what,
I think
yeah,
I think the classic framework of like the train example is just built for them to arbitrarily pick frames and do math with meaningless, right? There's no stakes. It's not in reality. That's why I like when we add some real stakes to it, like say a bomb or a real life train that's going to explode. The arbitrary math that you do for the timing difference within your reference frame really amounts to shit. And you can see that when you're like, oh, but wait, I still die though? But I did the math. No, you still die. It's like, oh, relativity. Oh, I get it. Like that's how you do it. Otherwise, like they had no stakes. They were just allowed to do arbitrary transforms and coordinates that's based in nothing. Like that's what the course was designed for. That's why there is no real stakes in the classic train example, I think.
yeah, yeah. And there's even a contradiction in the example too, based off of the only way that you could get C as the starting value to be C that in the reference frame of the moving train would be to treat it as being stationary. That's why Bennett goes into the analysis that relativity is only valid in statics, which means that all the frames are stationary, because you can't even do the analysis because right off the rip you're using C plus V.
Yep.
The only way to not do it is to treat the train as stationary. So it's so insane. And then they end up accounting for the timing difference anyway to make both frames agree on the simultaneous event. And they're like, look, the train blows up and everyone's fine. I wouldn't get on it. And it's like, ooh. So absolute space then? And they're like, no, but I don't understand what I did wrong. I did the math. And it's like,
Yep.
yeah, but you did it wrong and then physically interpreted it wrong. Because it's not about correcting for the timing difference for when the information is received. That doesn't help it. So anyway, what they say here, what they go on to say, is that yet many of these same students also have the deeply held underlying belief that simultaneity is absolute. And when the signal time is accounted for, all observers in all reference frames agree on the time order of any two events. So this is where they're running into problems, because if all observers agree on the order of events, then that means that simultaneity is absolute. And if simultaneity is absolute, you can't have consequences of the constancy of C being link contraction and time dilation. So earlier when we looked at the units of measurement for time, length, and mass for absolute values, we now have the new definition, which is dictated by a transformation of the rest mass, the rest time, and the rest length, the absolute values, with respect to the gamma change in them as a function of their velocity. So with E equals mc squared, the faster you're moving with your velocity, or with your mass, a function of your velocity is going to change your mass due to that equivalence for the energy of that velocity. And then so length and time are also going to change as a function of link contraction and time dilation, which is your velocity squared over c squared. So we're moving on. So this is the deviation from the classic here to explain all this. And again, Einstein is just reiterating here in the 1940s about how Lorentz physics, Lorentz transformations are what's going to dictate inertial frames. And using the principle of covariance, we're going to satisfy these transformations following this symmetrical framework that we're not going to violate. And as long as we're operating within the symmetry of the framework, then we can show that we can show that the laws of physics are invariant under transformation, which is important for them for substantiating how they make the assertion that, well, in this reference frame, XYZ would happen if they've never been to said reference frame, but they could math it out what it would be if they do it correctly and symmetrically and follow all the rules. They can, now it doesn't mean it's true, right? But if they do it correctly, that's what it would be hypothetically. And in some cases, it makes the correct prediction, and in others, it doesn't, and they have to make further adjustments. But we're just going to stick to the basics here. So we're going to get introduced to the idea of satisfying covariance. So covariance, defined by Einstein, was done algebraically. So those transformations we were looking at earlier with the coordinates, it was manually algebraically breaking it down. Now Minkowski comes along. We've all heard of Minkowski spacetime. What does that mean? How is it different from Einstein spacetime? Well, it's the same thing, but it's just a different way to look at it in terms of geometry instead of algebra. So to satisfy covariance in space-time symmetry through algebra, you have to use the space and time coordinates and algebraically work this out, where where the distance and time axis change proportional as the function of their velocities. Now, what you could do though is you could take a graph and like plot out what this transformation would look like. So you would have your starting t, you would have your your absolute time, you would have your no change in time, your zeros would be here for time, your zero for your distance. And then you would have your change in distance and time right here, which would be represented by this hyperbolic curve right here, because this is hyperbolic, this is quadratic terms. So we're going to get quadratic solutions out of it. So the curvature here is going to be represented by this hyperbolic curve. And if you take this and kind of rotate it 360 degrees to itself, you would get this cone. You would get a cone shape. So Minkowski says that anything that happens in this cone, so basically if you don't violate the speed of light, anything that takes place in this cone is automatically covariant. You're going to experience it that way. So instead of doing the transformations through algebra, we're looking at it through like a geometric property of this light cone and curvature in the light cone to describe the link contraction and time dilation. So as the faster you're moving, the more you're moving up in this cone. So you're going to get more contraction and dilation. And then we get into, so that was the original theory, right? Starting off with just a simple coordinate system transformation. But then we get into what we have over here on the right, which is represented by absolute differential calculus, where moving forward with the ideas of total removal of this like absolute frame, because remember, they still needed one, at least for acceleration, for rotation frames and whatnot. And so anyway, to further like get rid of this concept and introduce how gravitation will complete the explanation that the relativity theory can provide, because relativity theory only applied to the uniformly translatory motion frames. So Einstein here is trying to apply it to rotation and linear acceleration. And he's going to do that instead of using link contraction and time dilation as a function of velocity. Acceleration and gravitation are going to be equivalent, and as a function of the strength of the gravitational field, that's going to cause what would be link contraction or time dilation in that field. So with mass and energy equivalence and all that, so mass, energy, momentum, and all these things, you can turn that into a singular value of a gravitational field. And then that gravitational field, so on the right-hand side of this equation, of these field equations, we have this tensor, T mu nu, represented by represented by T mu nu. So this is the mass energy momentum tensor. And what they do here is this is the boundary condition for what you're going to be calculating. So remember how they're not going to assume an absolute fixed frame. That would be crazy, right? They have a philosophical bias to that. But what they will do is they'll assume the mass and energy distribution of the universe so that they can convert that into a gravitational field on this side of the equation for their parameters. And then they're going to use this space-time stiffness, which is going to be basically describing how much gravitational, like what the strength of that gravitational field is, how it's going to curve space-time over distance. And then over here on the left-hand side, the big G mu nu and the minus lambda G mu nu is the lambda, starting with that, is going to be the cosmological constant for dark energy. So they can just turn that on and off depending on what kind of calculations you're doing there. But the big G and little g mu nu are going to be your variables that describe, or your tensors that describe space-time curvature as a function of how much uh, energy was conserved into that gravitational field. So to start this, you just need, forgetting absolute time and space and everything that was done before, because we're not going to do that. We're just going to assume that everything's in motion, and we're going to assume the mass of the, we're going to assume the energy distribution of the universe, so we can have a homogeneous system, or, well, if we need a homogeneous system, however we need to describe the system, we can impose the conditions that will give us the correct calculation. And of course, this is built on absolute differential calculus. And what that means is, so this, on the left-hand side here, we have space-time curvature. Space-time is represented by a manifold, right? So we've heard of space-time, we've heard of space-time curvature, we've heard of manifolds. Well, this is just describing the, how much curvature is in that system. So if we think of a geometric structure, I kind of think of it like, say you're on the inside of a basketball and you can see like the dimensions of the basketball from the center of it that you're in, and you can see the curve of it. Now, let's say you start doing math of little sections of curve, well, any section that you can define along the curvature of that manifold. And because you're deriving it from the curvature of the basketball itself, like the inside of it, you're automatically going to be covariant. You're automatically going to be in alignment with the system that you're using, because you're going to have dimensional consistence with the manifold. So what they can do is, once they have the energy of the system, they can conserve that into the gravitational field. Then the gravitational field bends space-time curvature, so they've got their overall universal structure that they can work with. And then now, once we have that, we could take little infinitesimal sections of that arbitrarily and define anything we want, any spatial distances in between, anything, light years, gigalight years, whatever, parsecs, doesn't matter, right? Because we have the initial structure already good to go. We can now do this. So now, inside of this structure, inside of this coordinate system, we can use coordinate labels to define points. And then with these points, we can draw straight lines in between them two other points, and we can describe how much curvature would exist between these lines when we're doing these angle relationships between these points, based on the properties that we're assigning to the points in terms of the mass of the things in question. Now, it should be noted that when we move forward, that the coordinate labels are not dimensional values. They're not real things. They're placeholders that they use. They don't have dimensions. Now, all of this might sound intimidating and confusing, and, it has a lot of fancy stuff on it, but all this is just a dressed up version of, don't look here, there's no absolute space, but we're just going to assume it the same thing in a different way, and then not tell you that that's what we're doing. But because if you have the freedom to set the boundary conditions and input conditions of your equation, then it doesn't matter. You can get this to calculate anything. So the relationship of satisfying covariance doesn't mean anything. If everything is covariant, then nothing's covariant. And that's what happened here with this. But that's what had to be put forward, because we have to remove the idea of absoluteness. And then this ended up getting Einstein in trouble, because to satisfy conservation laws, with mass and energy being the same thing, and then that being a result of a gravitational field when you try to conserve it, you get into dimensional consistency issues where Einstein ended up writing Lincoln Barnett in 1984, who was a physicist who was critical of Einstein. And he was like, hey, this is Einstein here. He says, it is not good to introduce the concept of mass, big M equals little m divided by 1 minus v squared over c squared squared of the moving body for which it has no clear definition can be given. It is better to introduce mass as the concept of rest mass, meaning the lab frame rest mass, the Newtonian concept of absolute mass, the thing that he's at the point in his life at this point in the 40s here, where he's been trying to solve this for a number of years, can't do it. And so he's like, let's just say that there's an absolute mass. Absolute, you say? Interesting. Instead of introducing capital M, it is better to mention the expression, or to use this for the expression of momentum and energy of a body in motion. So making a distinguishing factor between the two so that he can satisfy conservation laws later on. But what was done specifically in terms of seeing if this theory is physically meaningful or not, a man named Stephen Crothers in the early 2000s was pursuing a PhD in general relativity, and he was doing a dimensional analysis on the tensors. And before he did that, he was specifically doing an analysis on the Schwarzchild metric and black holes. And what he found is that modern astrophysicists and cosmologists are misinterpreting how they're using the equations that they're using. Earlier, we talked about the labels that are used. Well, in the Schwarzchild metric, which assumes certain boundary conditions, which we'll go over later, but the relevant part here is that to describe the black hole, they put in their coordinate label, which is just defining the point in the coordinate where they're, starting things off, right? It has no dimensions to it. And then they're just saying that if they use that as a radius value, that if you calculated the gravitational potential there at this non-existent radius that they've derived from a thing that has no physical dimensions, they say that the gravitational potential there is so great that it exceeds the speed of light, and that light can't escape from it. This is the backbone of like the jumping off point for how a black hole even is calculated, right? Because we've all seen what's that Matthew McConaughey movie where they're traveling in interstellar space and they're looking for a black hole, and the guy, he finds his daughter through a bookcase after time traveling.
Interstellar.
Interstellar, right? So they got this movie, right? We've all seen how cool that is, and the concept or what they're putting forward. How this was calculated would be like the equivalent of like a math mistake in your Excel spreadsheet that gives like a 0 value, and you're like, oh my god, the value here just this breaks everything. And then instead of just like realizing that you made a mistake. So how you would actually do this, per Crothers' critique, was that you would have to assign another coordinate label, and then do an integral of the distance between them to determine the radius value, which makes sense. And then anyway, when you do that to get the radius value, you get a different radius than what they predict using, misappropriating the coordinate label. And it doesn't lead to a gravitational collapse where light can't escape. There's still an increase in gravitational potential, but it doesn't lead to the contradiction that they've imposed and philosophized and mythologized and canonized by measurement through interferometry. And we'll see what a problem that'll pose for them as we continue. So Crothers makes this anecdote at the end here of his analysis. And then after he goes through like several different back and forths with, so let me go over this real quick. He gets expelled from the University of New South Wales over this analysis because as he's presenting it to his superiors, which are supposed to be sponsoring his PhD candidature, they're like, we're not going against relativity, dude. We can't sponsor this. This radius value is our radius value. You don't take my radius. Guys, we've been battling globe Earth, flat Earth radius values. Crothers was battling radius values in black holes. The R value. He falsified the R value in the cosmological sky demon that eats light. And so so anyway, the only way that they could critique this man's work is if they could change what he did when he submitted it, and then critique the changes that they made as if they were originally presented by Crothers. And Crothers was like, "Whoa, this is crazy. Why are you guys doing this?" So he ended up escalating and complaining and taking us to the faculty board of New South Wales and all this stuff. And throughout this whole thing, they ended up determining that, he was going to be expelled, and they never address why that guy was allowed to change his work and then present this as if it was invalid. And it got to the point where he addresses the International Gravitational Committee, which is this relativity committee that's in charge of determining how the equations are interpreted. Because there's only three solutions to Einstein's field equations, and so they have to have like a unified way of like interpreting it and all this stuff. So there's a committee for this thing. So Crothers is in a back and forth with him about this. One of the committee leaders, this guy named McCullen, and McCullen does the same thing that the guy at the University of New South Wales did. And Crothers is like, dude, what is going on here? This is insane. And he gets into back and forth with other cosmologists who acknowledged what Crothers is saying. And they're like, no, we're not using this as the R value. That's crazy talk. And then you could go to their website, like William DeSitter, and see how they're using it specifically as a radius value. So it's like, they're all aware of it, and then when they get called out on it, some of them will admit to it. Some of them will say that they're not doing it, but then when you're not around, when you're not looking, they're like, yeah, it's the radius. So we'll get to his
Whether or not you know this fact or not, right? If you don't know,
if
then
you
we'll
don't
use
know,
it.
if you don't know,
Yeah.
then woe to you. So a simple non-mathematical proof, because a lot of what we went over is kind of intense, but now we'll go over like the meaningfulness of what is described. So earlier I said that there's only three solutions that are valid for Einstein's field equations. One is the de Sitter universe, one is the Schwarzchild metric, and one is the FLRW metric, which describes like the Big Bang theory, the so-called homogeneity of the distribution of mass and energy over the 14 billion year timeline based off of a explosion out of nothing. All of that comes out of the solution derived from the FLRW metric. Black holes come out of the Schwarzchild metric and the Kerr metric, which describe black holes that are either stationary and non-rotating, or black holes that are rotating. Singular black holes or black hole pairs that are rotating and colliding and stuff like that. And then the other one is an empty universe solution. I'm not sure what they even use that for, but so there's only three solutions to it that they use. So, and because of this relationship there, and because of how you have to define these boundary conditions, like starting with the energy distribution of the universe to describe the curvature of the manifold, to then determine how much curvature is happening between bodies that you're using, right? To get to that point, you have to use these non-linear field equations because everything is determined in this tensor value. Because this mu nu here, these two values up here above this t, these are little matrices that you fill in the values for what you're going to be describing for the energy of the system here. That's how that all breaks down. So everything is contained when you do your initial calculation to start your jumping off point. So you can't solve something in a Schwarzchild tensor and then add it to something to like add it to the mass of the universe in the FLRW metric. Because remember, mass and all these, there's no absolute or anything like that. So we can't do mass addition like that. And these are nonlinear equations. So they don't give linear solutions. You can't derive something in one and then impose it in another. They're derived under completely separate conditions. That's the hugely important takeaway to this. So he goes on to say here that it is very easily proven that black holes and Big Bang universes contradict one another, and so that they are mutually exclusive. All alleged black hole solutions to Einstein's field equations pertain to a universe that is spatially infinite, are eternal, contain only one mass, are not expanding, and are asymptotically flat or are asymptotically curved. But the alleged Big Bang universes are spatially finite or spatially infinite, are finite in age, contain radiation and many masses, black holes, some of which are primordial, and that also includes expansion, depending on how you want to do it. And sometimes they can have conditions that are not asymptotically anything. So it's just a homogeneous distribution all around. So thus the black hole universes and Big Bang universes contradict one another. They are mutually exclusive and so that they cannot coexist. It is therefore not possible for black holes to be present in Big Bang universes or even in other black hole universes. And likewise, it is not possible for the Big Bang universe to be present in a black hole universe or in any other Big Bang universe. Nonetheless, astrophysical magicians superpose black holes and Big Bang universes, notwithstanding that they are incompatible by the very definition, and that the principle of superposition does not hold in general relativity. And the superposition there would be what I was talking about earlier with being able to do mass addition over the systems and stuff. Like you can't. These are nonlinear equations. Can't do that. Much of modern physics is simply manufactured in this way, and so it bears no relation to the actual universe. So when they get into units of, I'm sorry, any questions or comments on that?
I like
No,
the
that was
term astrophysical magicians. I think we should shorten it to astrophysical magicians or whatever. I like that his whole stance agrees with ours from that. Just that one phrase he used.
Yeah. Yeah.
I
So they've
think
got,
it's so interesting that, in higher academia, you still have people that are being blatantly dishonest. It's just sad. They
yeah.
shouldn't be holding these seats. They shouldn't. That's not what academia is about. It's about gaining knowledge and learning the truth. And this is
Yeah.
ego. This is just straight ego.
Is it
It's
though, or
sick.
is it
Dude.
about gaining position and then retaining that position? That's
Dude,
weird.
Yeah.
I think maybe
Dude.
people have different goals then.
The Crowther story is wild because they go on, like when he goes and talks to the because he's writing letters to this dude and like submitting his math and papers and stuff to the International Gravitation Committee guy. And this dude writes him back and he's like, ha ha ha, you think you're smarter than Einstein? Why don't you take a seat, young blood? You don't know anything. Many men much smarter than you thought they were smarter than Einstein, and no one is smarter than Einstein. And it was like, and then on the back of that, he goes on to like do the same thing where he couldn't refute his math, so he made his own changes to what was presented to him, and then critique that, and as if it was what Crothers presented, and was like, "You're so dumb, you don't know anything." It got crazy, dude.
Glober gaslight from before time. They've been doing it the whole time. It turns out.
The craziest gaslight, bro. The craziest. So yeah, so now that we know how the theory works, where the reference frames applies, we can experimentally falsify it and be rid of it for future generations. So when we have an apparatus where the observer and the source emitter are fixed to a specific spot and then it's in uniform motion, there's no relative motion between the source and the observer. They're always, equidistant from one another. So the relativity theory, and even Einstein stated in his 1905 paper, that any closed polygonal circuit in uniform rotation at a constant velocity would be, his equations would apply there. So Sagnac came along in 1913 and was like, I got you, bro. Let me put this source emitter here fixed to the rim and put an observer fixed to the rim here. We'll rotate this, calculate the path length, the area that light had to travel. We'll input the angular rotation rate here, and we'll measure the phase difference in the speed of light like Michelson and Morley did, except our apparatus is going to show the proportional phase difference with respect to the rotational rate instead of just being stationary and seeing what we measure in the phase difference over 11 meters. And he measured the rotational rate proportionally exactly. So the speed of light was faster and slower, directly proportional to the rotation rate. So in other words, it got a velocity boost and it got velocity retardation depending on whether or not it was going with or against the rotation. So this was evidence that there is a preferred frame, that there is an ether. Sagnac actually called this an optical vortex, that the ether was in rotation, producing this, clock, so that like light traveling through this rotating ether is going to be retarded or velocity boosted. That's how he described it. And this completely falsifies Einstein's relativity theory.
But I thought
And
Sagnac effect proves relativity, like everything else in the world.
so only when you use a fictitious reference frame at the center of this device using a cylindrical coordinate system that you're going to overlay on top of it and then impose the conditions where the motion is actually relevant to the midpoint so that you can have a first order timing difference, not ascribing any link contraction, obviously, but using the distance change. So using absolute space to preserve the distance change using this fixed midpoint as the reference. That's the only way you can do it, and it's explicitly against what Einstein said how his theory works.
As a Glober, I'm still okay with all that.
Oh, many people are, because it's the only way to maintain it. And then so Ruyong Wang in 2004 did the same thing that Sagnac did, except he used a linear configuration where he used a fiber optic gyro cable and unwound it, came up with a configuration where only this top portion moves, and a configuration where in a conveyor these move together, the detector and the source in the top portion. And so in such a way that there's no relative motion between them according to relativity theory, and the motion's measured every time, directly proportional. We're looking at the graph to it. So the faster you move this, the faster the fringe, the faster it measures it measures it exactly. So this is a direct refutation. This means that independent of the configuration of the apparatus, meaning if it's going in a path length that creates an area, or if it's creating a cross with orthogonal angles going there and back to itself, doesn't matter. They all measure the same thing. They're all valid. They have different levels of sensitivity, but the measurements are the same. So in 1940, the Sagnac experiment was repeated where the source emitter and the detector were fixed to the lab wall and using 45-degree angled mirrors to a platform that used those mirrors to deflect a split light beam down to a rotating platform that had 45-degree angled mirrors on it that would send the light back to the top, that would send it back to the lab wall. So there's absolutely no relative motion between between the source emitter and the detector. The only thing we have is this rotating plate down here. In the proportional velocity of the rotating plate was measured in the stationary frames where relativity predicts that the speed of light is constant and that it would be independent of this rotation down here, and that the speed of light would be measured with no fringe difference. Now, using no preferred frame and trying to calculate the distance or the fringe displacement, relativity is off by a factor of 10. So it cannot make the prediction unless it uses a preferred frame at the center to have the first order timing difference. So link contraction and time dilation are not predictions that have the ability to explain interferometric measurement. We have here the Sagnac challenge, where relativists are trying to prove there is a relativistic derivation for the Sagnac effect. In other words, they want us to believe that the theory that says an inertial observer will measure the speed of light being constant, they want us to believe there's a way that they can derive it so that an inertial observer that's supposed to measure the speed of light as constant will measure it as c plus or minus v. So let that kind of sink in for a minute, and then here's the attempt that was done by PhD Blitz, who has a TikTok and YouTube channel. He does, modern science education stuff where he presents the correctness of relativity theory and quantum electrodynamics. And what he did here was use a Minkowski cylindrical rotating system. So we're already off to a not great start using a fictitious reference frame with the center midpoint here where the measurement didn't take place. And then he's going to say that we can transform that to a rectangular coordinate system. Okay, so we got our X, Y, Z, T dimensions for everything. And then from that, we're going to use C times the radius times the angular rotation rate plus or minus 1, which comes out to describing C plus or minus V with respect to the midpoint of the coordinate system. And he essentially said that the physical explanation of this is that you could put the detector at the center of this coordinate system where the radius starts, and then you could put the emitter at the or you could put the detector or emitter at the center there, and then at the end of the radius, you could put the detector or emitter there, and then you rotate the coordinate system around them, and this allows for the first order timing difference. And that is not so. I don't see a Lorentz transformation in here to like start us off with like the main point of contention, other than the fact that this is a classical equation that describes c plus or minus v with respect to rotation clockwise or counterclockwise, the, which assumes absolute space for this to be relative to. This is not a Lorentz transformation. This is a Galilean transformation from a cylindrical coordinate system to a Cartesian or to a rectangular one, and then saying that it's just spinning. That you could have just kept the cylindrical one. The contention wasn't that you could do that and then use the classical equation. That's insane. There's no way to predict the Sagnac effect for relativity theory. And so this explanation is invalid because if you try to use the Lorentz transformation and you predict no relative motion, the maximum fringe displacement that you could predict if it were possible for you to measure it as a third-party observer relative to that system in motion would be that you would measure link contraction and time dilation, to the much smaller degree because it's a function of the square of the velocity over c squared, not a first order effect. So the conclusion of all this, and in regards to how GPS works, where we have a constant real test of Einstein's thought experiment with the embankment and the lightning strikes, with GPS signals being sent from either space vehicles, so-called, or GPS stations, so ground stations. They're all sent at the same time. They're all using a universal timeline. So observers that get their signal at the same time relative to stationary observers as they intersect would require, would require corrections for relativity of simultaneity, because the event in which these signals were sent, the timing would be different according to their velocity. But no such correction is ever presented, and it would absolutely have to be given the precision of GPS. They measure down to the millimeter. You could do it even more accurate with the military stuff. So that wouldn't be possible if they had these variations and corrections, because the timing is how they derive distances in GPS, because it's a timing interval system. So this would if this correction existed and had to be accounted for, it would throw everything off. It's never accounted for. You can read through the ICD Navstar documents. You'll never see a Lorentz transformation in there. You can read through Neil Ashby's work on how accounting for the Sagnac effect is proof of proof of relativity theory, and you'll see that they use Galilean transformations from the ECI to the ECEF reference frame, meaning they use absolute time for their transformations. They're not using relative time. They're not doing the thing that they say is the backbone of what they now believe in. They're using the thing that they used to believe in before they took the measurements of Earth and that conflicted with their cosmology. And they're just lying about it. So in conclusion here, time and space are absolute. Trading time and space for stories about how the mass distribution of the universe, it will satisfy tensor calculus, so that so that choosing reference frames is physically meaningless, is an invalid interpretation of reality. Even with all that math, simple first order measurements with V over C can't be explained without invoking mass distribution of the universe or using a preferred frame. So they've never escaped this. They've just ignored the measurement at face value and then built a lie on the top of it and use asymmetrical analysis now to further facilitate it, like measurements of the muon and stuff. They don't adhere to Lorentz symmetry in the analysis, but they use it as proof of the theory. Well, the fact that they don't do it symmetrically is proof the theory isn't real, isn't physically meaningful. It's just kinematics. The laws of mechanics are not singular, and they are only satisfied with the respect to the lab frame. So earlier we read that the laws of mechanics, right? So not just talking about the laws of motion, we're talking conservation laws, energy prediction, all of that. All the stuff that we went over earlier is only valid with respect to the lab frame. So shout out to Cass, who proposes the absolute lab frame in flexible ether to explain the measurements to be the dynamic cause of the measurements that are made with respect to a stationary fixed Earth. And that is the presentation, lads. If anyone has any questions or comments, we can certainly get into them. That was a lot.
Great. That was a lot. That was a lot of math. That was a lot of physics. That was a lot of history. But I mean, so space time, right? As you started with coordinate systems being sort of arbitrary, pulling up cylindrical, pulling up spherical, pulling up what we need to remember is that when you're using those coordinates, like say if I made an observation of a star, right, in my hemispherical view, I could transform that real observation to be displayed, with different Cartesian, like in spherically, I could do it, and transformation to do cylindrically, I could do a transformation. It wouldn't matter. The dimensions and the distance would all be proportioned. It would all be covariant, if you will. So that's why that Cartesian simultaneity makes sense. But when you invent a new coordinate system, and the only purpose is so that the math will work out and that my transformations will have, covariant input and output. That is the purpose of it. It has no physical meaning. It has no tie to reality. How do they get away with that then, therefore, having meaning? Right? Because if it has no tie to reality in space-time is a coordinate system that we invent to do math, then they're like, oh, but actually, the curving and warping of space-time is creating a geodesic arc that is the dynamic cause of gravity. Like, how do you reconcile all of that together?
You actually can't. It can't be done.
It's making my brain hurt to even articulate what I think the position would be. So it's like, so it doesn't matter, but it does matter. It's everything but nothing. It cancels out, but it means everything. Hold on. Wait a second.
It's preposterous.
So it shows how long they've been doing this stuff.
Yeah.
Yeah.
Like if you argue with a relativist, they will argue for the validity of space-time, I think, with with vigor. Right? Absolutely, it's real. It matters because we can do this math in it. And it's like, well, no. It would have to have some sort of datum to tie it to real-life observations. It can't be based via a thought experiment, right? Which is how space-time came about. And then the coordinate system to be put in arbitrary nothingness. You can do 3D number lines in space over nothing. Like, how do you then say actually that is the physical meaning of everything?
You just have to believe in it because the math is so complex and you're solving it, and your life would be meaningless if you just spent all that time solving something that didn't mean anything.
I mean, I get most
You
people,
would be considered crazy if you thought it was anything else.
Well, I get most people because they surrender their understanding to experts. They go, I don't know the expert. I don't have to understand it. That guy in a coat over there, he clearly gets it, and he's smiling confidently, so I know that I'm right. Still, like that's what most people have. But there are people in the field who have to understand what they're doing to invoke nonsense like this to maintain their belief system, and those are the people that I'm like, I have to question.
Yeah,
like, what do you believe in?
It was like those people that Crothers was interacting with. They couldn't even address what he was saying. And then he even got more advanced with it with some other tensor stuff that's beyond my capability to relay what he did. But it was like so in depth that like it's just not like their system's broken. And they've known about it because what he found, the issue that he found is an issue that they'd known about since the 20s. Like the guy that invented absolute differential calculus wrote about it. And then people just like forgot about it. A couple people presented their own tensors and they were like, oh, these ones, satisfy it correctly. But Crothers analyzed those too, and they all suffer from the same thing. It's a mathematically broken framework. It doesn't even do the thing that it is attempting to say that it does. It's all an illusion.
Not to mention that, like, the propaganda for space-time as a thing is ubiquitous through culture. You got, who hasn't seen a movie where someone takes a piece of paper and they take a pencil and they fold the piece of paper and they put a hole in it and they go, look, you see the Einstein-Rosen bridge because you can get over here. That's like, it's the basis of sci-fi. It's the web with which science fiction is woven. So the propaganda for you to believe that space-time is real and has real dimension as a valid coordinate system is literally everywhere through our culture. And I think that's crazy.
Yeah. All right. So let's see. Do we have any questions? Let me go through the chat here. Then while I pull that up, if there's nothing else to um, talk about on the Prezi there, we can get into what you got. You know how your week was, Zach and Shane, and we'll wrap up.
Someone said it's like Highlander time. Yeah, that's not correct, right? There could be only the rest frame.
There can be only one frame.
You guys know that they use laser beams to hold particles? Like if you take a laser and run it through one of those filters that converges it, at the
Yeah.
convergence point, there's a pressure mediation that's created, because it's crossing over like that.
Right.
Well, right inside that little nook will be a little pressure mediation, and that's how they like hold the particle there and then start accelerating it and make a trough to where it's not actually touching anything, the walls or anything, but it's still stuck in this spot. And you can do it with a laser beam. It's insane.
That's crazy. I'll
We
have to take
covered that on
take a
GLOEBUSTERS
look at
Tech
that.
on Thursday.
Last Thursday?
Yeah.
I'll have to look at that. I'm familiar slightly with that with the Einstein Bose thing that they do, where they use like a cold laser to slow down the particle or whatever, and then they look at it. And so, like, that's kind of like very similar in that regard. But yeah, I'd like to take a look at some of that stuff and see what they're actually doing because their interpretation's obviously insane, but they're clearly doing something.
Yeah,
I
I mean,
watch
there's a
most of that
bunch of
stuff.
demonstrations of it on just on YouTube, people doing it. They get a nice powerful laser, a culminating lens, and then all of them take a marker tip. I don't know what it is. It like burns the little bit of the felt off the marker tip, and they try to get that stuck there. And eventually they'll touch it with the laser, and all of a sudden you'll see a little piece just like light up. It looks like a sun sitting there, and then they can actually adjust the laser, and it'll move back and forth that particle. It's really neat. It's really neat. I had no idea that that's how they did it.
You guys did a bunch of stuff on that GLOEBUSTERS Tech about apparent versus actual in reality, holographic, like where things appear to be versus where they are, and the whole argument of where things quote really are, right? So that was a
Yeah,
really good
yeah.
one.
What are we looking at up in this? Most of it was about the sky. Like, what you see doesn't exactly mean that's what it is. Illusionists have been using these tricks forever. And then you go back to the biblical accounts and stuff like that of what the sky's made of or what it appears like. And yeah, I mean, it could be mirror-like. There could be all kinds of properties taking place up there and these are just pieces. They may not be the right puzzle piece, but you can't build the puzzle if you don't have all the pieces. You can throw away pieces that don't fit at the end when you get all of the puzzle there. Be like, oh, look, we got extra pieces. That's okay. But if you don't have all the pieces, then you're never going to build the whole puzzle.
I like that. I
Yeah.
like that because it addresses how people sealed off aspects of flat Earth learning for years in certain communities. Like, no, can't look at the sky, therefore you can't accommodate anything from the sky. Therefore, you'll have shitty arguments the whole time, or whatever. Is how that works.
Mm-hmm.
Yo,
Yep,
what's up,
gotta have an
Taylor?
open mind.
Yeah, I had a question about the Berry Center.
Yes. What's up?
The Dom tried to describe it to me, but can you try one more time? See if I get it this time.
Yeah. So if you look at the center of the sun, because like in the heliocentric model, they conceptualize that's the center of this, or everything is going around the sun, right? But everything also has its own mass and gravitational relationship that corresponds to that mass, and everything is also moving at different times throughout the year, relative to where it's at. So it's going to have a different amount of gravitational pull with respect to that center point on the sun. So throughout the year, as the planets move, they say that that mass distribution will change the gravitational midpoint where the two masses would cancel each other out, like the two opposing forces would meet. Now, it wouldn't be in the center of the sun because, it would be offset a little bit because it's a pulling relationship with the other gravitational force that they're introducing. So this would be where they collide and then they meet, like, they have like a null point. So it would be like not at the center of the sun, but it would be like a couple million miles away from the center of the sun is where they would say that that's where the gravitational potential, is a null point. So they would say that that point is stationary and fixed with respect to the universe. So if you could put an observer there at this gravitational null point, you would have this like mystified spot that is actually at rest. Now, the Earth not at rest, but if this gravitational midpoint a million miles from the center of the sun, still inside of the sun, but not in the center. This is where you could absolute rest there, but nowhere else.
Got it. Okay, one more question. How do they figure
Mhm.
out how much the planets weigh again?
Ooh, using this awesome relationship that I will have to do a little Prezi for to show you them to show it easily.
Isn't it just Kepler's law from Newton's law, and then a little algebraic trick swapping out a known mass, solving for m? That's how they do it. Without Newton's trick of substitution, it's impossible for them to guesstimate any masses of stellar objects.
Yep. What they do
That's really cool.
specifically to give you a visual of what Shane just laid out very eloquently is this. So starting with the, second, make it smaller. So starting with the mass of the sun here. Can you see this, Taylor?
Yep.
Is it not? There we go. Starting with the mass of the Earth that they got from the Cavendish experiment and the gravitational potential constant, this big G. So they measured the gravitational potential of the balls with respect to the canceled out gravitational potential of the Earth, right? So the way that it would all work out is that from this experiment from Cavendish, they have the gravitational potential between the balls, and that relationship also gives them the gravitational potential of Earth, or like the mass to produce that gravitational potential. So now they have two values out of this experiment. They have the gravitational potential exerted from Earth's mass, and they have the mass value to produce the gravitational potential. And then from that, they would, when you apply Kepler's laws, right? So the periodicity of things moving in the sky. So if you applied this relationship to the sky using the Kepler and Newton algebraic shuffle, you would take the periodicity of the sun, so just 365 days squared, and then that would be proportional to the cube of the semi-major axis of the orbit. So that would be your astronomical unit. That would be your distance from the sun to the Earth. And then when you do the algebraic shuffling, though, you can now introduce a relationship where you have G mm over r squared is how they write it out. So now we can do, where's my little m at? There it is. So now we have the periodicity of the sun. We can GMM r square this with that. So we have mass of the Earth and we have mass of the sun. We don't know the mass of the sun, but because it's algebra and we have the other necessary variables, we can work out what the mass of the sun would need to be to produce this orbit, so, with respect to this mass. So now we have the mass of the sun, and now we're still applying the periodicity of planets from our earthly perspective, but now we're applying the ratio to the, as if it was like, going around the sun essentially. So for all the measurements where we're saying this completes a circuit around the sun, it's just viewed from our perspective. So it's the same as saying the circuit around the Earth. But when it completes its circuit, now we can get the M value for it. So now we can measure how much, or calculate how much Mercury weighs based off of how long it takes to go around the sun. And then we do the same thing for Mars, Jupiter, Neptune, Saturn, whatever this one is, Mars 2.0, and Pluto or whatever. So that's how you could do it for anything, really, because it's just algebra. So it'll give you the calculative value, whether it's physically meaningful or not. And then that's why when you get into the algebraic shuffling here, this M, when you apply GMM, you apply the equation out to solve it, the little m actually cancels out, and it just becomes a ratio of the periodicity being proportional to the cube of the semi-major axis. That's all it's ever been. So that's how they do that. That's how they get the values for them. And then, like, when they got the value for Earth, like when they calculated what the density relationship would have to be, they were way off to produce the mass. So that's where they got the iron core. They just made up the difference with what it would have had to have been based off of a blind assertion. And now they have like a completely separate, model that they have to now deal with. That's backwards derived off of supporting a lie.
Yeah, I was gonna ask how they got the gravitational potential of the Earth.
Yeah, so from the Cavendish experiment, when they have the mass of the balls, which comes from the relationship with their weight, which you can derive from little g, because all they ever have is little g, this acceleration that we have on Earth. When they have the balls on the torsion beam, they're saying that they're canceling out the gravitational potential produced by Earth, so that there's none there. And then what they
I'm
then
not
measure,
following. I'm not following. I'm sorry, one more time. I'm really trying
yeah,
to get this.
yeah. So if you put balls on opposite ends of a torsion balance to one another, they're not going to be able to like hit the ground, right? They're going to stop. They're going to be held up by the torsion balance, right? Does that make sense
Okay.
so far?
Yeah, yeah.
So then they're saying that they let the torsion balance like be stationary for as long as possible so that it would become stationary. Now it never did become stationary. They took the measurements while it was in motion and just assumed or whatever. But let's assume like ideally that eventually if we let this thing sit long enough, it'll be stationary. And then what we could do is we could introduce another mass close to the ball, and then we'll measure how much the uh, how much the balance beam like moves to the other mass, and that will give you an angle. So they call that the torque angle, like how much torque is being applied to that wire that's holding the torsion balance to produce that angle. So when they have that angle, that's what they're using to get the rest of the relationship for the gravitational potential.
Okay, so they had a ball in a lab and they saw how long it took to fall,
No,
theoretically?
no,
Oh no.
they took how long it took for it to like oscillate back and forth, and they just took an
Okay.
angle measurement of that of like a really small deviation within the greater deviation
Yeah, there was
of
two
the
lead
angle.
balls and a rod connecting them, and then a wire hanging. So they were trying to get that to stop from swinging around. The two lead
Oh.
balls with the rod in between it. Yeah, they wanted that to stop from moving. It never did though.
Where did they even get the calculation that that would like work? Like that would give us like obviously the mass of the Earth, but like so did they use the calculation of like how long it basically dropping objects and how long they take to fall and the acceleration, or where did they get the fundamental calculation to like backtrack that to see the gravitational potential of the Earth?
Well, that's where they started with the little g with mass, because that's all they ever have in comparisons to things that are in relation to that. So they started with that and then measured an angle, used that angle as a ratio to derive how much force it would take to produce it. And then from that, they were like, this, behold, the gravitational potential between two bodies as a constant.
Did they mention in their paper that the ball never stopped moving though?
It's a good question. I have not read the full Cavendish paper.
That's really interesting.
I'm pretty sure they said that it was fixed, right? They had teared it out or whatever, but in respect to
Yeah.
anything, no, they really didn't. So that's the argument, right?
So they
That's
were
why
just
people say, no, they
like,
totally did, because they said they did, but when you look at it, no.
yeah, that's crazy. So basically they were just looking at how the oscillations changed over a period of time.
Yeah, and keep in mind there was a similar experiment done by Coulomb a couple years prior, who was doing it with like electrostatics. And so the purpose here was to nullify electrostatics. So they were using lead balls and then, discharged them and whatnot. And then they were seeing if they could measure like a smaller deviation. So if there was like a continued effect, irrespective of the charge potential, and they were just like measuring a smaller deviation in that, like none of what they extrapolate out of it would be physically meaningful, but you would get all the necessary calculative values to start applying everything with constants and do ratios of that. Because the only thing they use big G for is for the sky, for stuff in the sky, because if you try to apply it to anything else, like for physics and measurements, that's where quantum mechanics breaks down with gravity. What does that mean? Well, it means you can't use big G. you can't use their cosmological constant. So that's where it like falls apart on that scale on local measurements, and then in the sky, It fell apart with Newtonian dynamics, where with the perihelion precession and all that, and they had to, change it to the relativistic stuff. But either way you look at it, they got this value out of it, and then like now you got the value. Well, now you can play with it, you can do stuff with it and see what's up. But they only use it for stuff in the sky, and that's kind of telling because the only thing that they use on Earth is little g, which can be kinematically derived as a function of height and how long it takes for something to hit the ground.
Right, right. Yeah. Did they do that one with the electrostatics at different elevations or the Cavendish experiment?
Not sure. I don't think they. I don't
Good
think so though.
question.
That is a good question.
Oh, well, thank y'all so much. I really enjoyed it.
Yeah, absolutely. All right.
And that is the one and only way to, quote, calculate stellar masses. Without this trick, nobody knows what any planets weighs. Nobody knows the mass of the sun. Nobody knows like the mass of anything in the sky, right? Which of course is all guesswork at best anyway. So this is the trick that gives them the quote, the knowledge to lie to everyone about how they know how much planets weigh or whatever.
And just happenstance, they were right. When they sent things up there to all these planets and broke out their measuring tape, they were correct about everything pretty much.
They're always right, I
Right?
noticed. Yeah.
Dude, when they got their scales out and weighed the sun, what do you know?
Mhm.
What do you
Like
know?
we finally bought some galactic scales. We weighed the planet. Turns out we were right, guys. We nailed it again when we
Dude.
guessed back in the day.
Dude, the
That's
funny
awesome.
thing is them trying to weigh exoplanets. They're just looking at a small light shift in the star, like a
Yeah.
small little deviation in like
So-
either the movement of the star or the light of the star and how bright it is. So it's crazy. All these assumptions they make about these exoplanets. I was reading about it on their own websites. Like not even like just trying to get a genuine steelman, and it's freaking ridiculous.
Dude, Shane, what's that quote about steel manning mainstream physics and globularity has become like a comedic pastime?
Yeah, like we just for,
like if
for
you-
fun time and
if you-
jokes, we just steel man the globe hard.
Yeah, if
And
you
the
want
harder we steel man, the more we laugh. So it's just gotta go on.
Dude, yeah, if you want a good laugh, just start understanding how they weighed an exoplanet. So they just looked at the light fluctuations and came up with a periodicity of when it returned to a similar color, and then determined that was like a movement of it. And from that, they got their periodicity ratio, where they got their distance and orbital parameters, and then from that they introduced a little Newtonian shuffle, I call it, and then they got the mass of it. Oh, no way! That's so
Well,
cool.
dude, don't even forget the supposed method for detecting an exoplanet is to look at a star really hard, and then when it flickers a little, the transparent change in luminosity, you then speculate wildly about what that means within its
Yeah.
gravitational pull of the black hole that's pulling it around. So then you get to say, well, actually, here's what it means, and it's the mass, and it's not only another planet, but here's what that planet weighs.
That's crazy. It was only like news recently, relatively recently, that they've actually seen one of these exoplanets from Earth, from like an Earth-based telescope. And then I like dig extremely hard to find this picture, and like it's like a few pixels, and I literally could not differentiate it from a star.
No way.
Dude, that's hilarious. You got your first experience exoplaneting. That's
You're gonna start
epic.
selling us real estate
Dude.
from new exoplanets soon now.
Isn't that awesome how they make this bold claim and then like you go to look into it and it's like, here's a pixel from MS Paint. This one's gray and this one's a slightly different shade of gray.
You know, it changes from gray to not gray for that 1 second. That's an exoplanet. Just detected it, baby.
It's even
then
funnier
this-
that they try to make assumptions on whether life could be there or not, just like based on like the tiny twinkle in a
Yeah, the
star.
math equation for determining the likelihood of life evolving on this
Dude.
exoplanet of whose
Yeah,
mass we
dude.
just determined.
Oh man.
It's crazy.
That's so cool that
true.
they have an equation for it. They don't have an equation that would set a hard radius value that would be falsifiable for refraction or anything like that. But they have a statistical probability of whether or not life would spontaneously occur on a gray speck or a gray pixel
Or a twinkle of a star.
because of a perceived light in the sky. Very cool.
The funniest thing is whenever you actually look at these stars, and how can you make any assumptions? Like they're constant, like they're twinkling, period. So like to say that there's a slight shift in like the light spectrum or like it like deviates a little bit is crazy to me. Because if you're actually looking at these things, they're not like some like stable little light source. Like they twinkle in many cases, right? Depending on where they're at in the horizon, they could twinkle more or less. But either way, they're unstable. Like to say that you can make all these assumptions from it is wild.
Oh yeah,
Well, what
even
if I
like the
ratio
James
the rate of the
Webb,
twinkle?
What if I
the
ratio
James
the
Webb,
twinkle rate, Taylor? Does that change anything?
Bro, it's hilarious.
yeah, the James Webb Telescope people even said if we showed you what we got from the telescope, it looks like a black rectangle with some white spots on it. And they add everything else into it with data that they're given. And they add all the colors and all that kind of pretty stuff. But yeah, it would be a black rectangle with white dots. Like if you took your camera and pointed up at the sky and took a picture, that's what they see. The rest is all magic, right?
Amazing.
It's
It's all
crazy.
art. Someone's
It is.
artistic job is to make that pretty and gorgeous to make us all like allured by it, right? That's someone doing it really well.
Yeah, it's annoying. All that brain power, all those smart young people that have dedicated their lives to Narnia.
Getting
And we
narned
talked about
up.
that last week, right? Like when you the smartest people get attracted by theoretical physics as a field, when you get to go play
Mhm.
guesswork and do nothing, and contribute zero to society, but get the esteem of all the colleagues. Like what kind of a inverted society is this that we praise that?
They can't have them looking into real stuff. Might figure something out then.
Right, no ether, no wave theory. You know what? Light's both a wave and a bouncy BB that interacts with everything and nothing. Go figure out some science and use some magnetism. Here you go, off to your lab. You want some funding? Yeah, you're not gonna hurt anyone over here in the corner or whatever.
Here's a magnet. Don't ask us how it works. It involves in solving unlimited Feynman diagrams.
The physics foundation they give people to go quote invent an experiment is preposterous, right? So that's why they're not worried about people hacking into. Oh, did you accidentally discover etheric energy? No, we know you didn't.
We know you didn't. Oh.
Yeah, excellent presentation, Alan. Excellent questions, Taylor, as always.
Absolutely. Yeah, to really understand this stuff, it's a lot of learning vocabulary words. It sucks. It
Yeah.
really is. It took me so many times watching certain videos, and then watching it over and over and over and looking up this word. And when you're 45, it's hard to learn new stuff. I don't, you guys are younger, so you're not there yet. But yeah, it gets harder and harder to like hold on to new information like that.
I don't know, man. When I hear my friends using words I don't know, I get excited. I'm like, ooh, somebody hit the thesaurus. Is that a word I have never heard? Let me go look that shit up. I don't want to get one up by my boys. Hold on.
uh, but yeah, don't get
But
frustrated if you don't understand the first time. And always ask questions.
I think it's that curiosity that you need to maintain. Otherwise, you're not going to want. Like, if you don't want to
Mhm.
understand it, you won't. Clearly, right? So,
Yeah.
if you want to put in the time and to actually learn, and maybe to ostensibly articulate the argument to someone, right? Maybe that's your goal. So you got to learn it enough to be coherent with it, to present it cognitively, coherently to someone that you want to understand it, right? That's a goal. So to do that, you watch it 2 or 3 times. You go look up some side stuff. You do some research. You read the paper yourself, maybe, right? Develop your own context from which you want to analyze. I mean, you need that intellectual curiosity in the first place to spark any of that. And I think that's really what our goal is, right? To inspire that in people who are capable. I think that's probably how I frame it.
Good way to put it.
Yeah. All right.
Planting
Well,
seed.
you guys trying to wrap up for the day?
Sure.
Awesome. Awesome.
Yeah,
Zach,
great
what do you,
presentation, man.
yeah, thank you, sir. What do you got coming up this week?
I'll be on 5 a.m. Monday, Wednesday, and Friday over at Iron Rail Media. We do YouTube, Rumble, and freeworld.fm. It's
Nice.
a online radio type thing, truth thing that one of our buddies is trying to get get going. It takes a lot to get these things off the ground. It
Yeah.
really does.
Certainly does.
But it's going. So, but yeah, and then Thursday night we'll be doing GLOEBUSTERS Tech. Not sure what the topic will be. We'll find something.
Nice. Awesome. Taylor, what do you got coming up this week? And what did you do last week?
I presented on abiogenesis and debated, and it was wonderful. And I'm open to debating anybody else on the origin of life and how naturalistically it's impossible and unexplained without any sort of intervention. So if anybody wants to debate me on that, absolutely, I'd love to. And also Tuesday at 1 p.m., I'm going to be going on Dom's channel to give another presentation.
Nice. That's
Gotta
awesome.
keep the Czech Ether Cos branch happy. They're ravenous for content, I gotta say.
They're very hungry lads and ladettes over there. Very eager. All right, Shane, what do you got coming up this week?
We're doing Eratosthenes, I think, on Tuesday, presentation, which will probably maybe do GLOEBUSTERS after that. And then we got TikTok nights, maybe Thursday, Wednesday, Thursday.
Doing a little ticking of the talking.
Yes, yeah. We got to go to the worst part of the internet again.
hey, we can celestial theodolite everyone over there.
Just beat them over the head with it some more. I'm down for that.
Oh, we didn't
That's
do
fun.
the celestial theodolite. Well, we'll cover it next week. All right, we'll have
some fun with it first.
We'll have a more refined version give to everybody. All right. Well, we'll see you guys next week. Later.
Later, all.